More people there. People have come from there. Huh? They've all come. Huh? That's it. Understood. Understood. So you give me, you tell me when to start.
We should hit 40 minutes that time. No wonder.
Off sync.
Time 40%.
Lunchtime.
Just tell them to switch off the phones. It's likely people forget to do it.
Yeah, okay, okay. So may I please ask people to put your phones on silent? I should do it myself. 9:05. Okay. Just ask Arka if it's okay, and we'll get started. Not here? Okay. So, good morning, everyone. My name is Vinod Ganapati, and I'm currently the chair of this department, the Department of Computer Science and Automation. And on behalf of our department, it's my pleasure to welcome you here on this really special event centered around the visit of Professor Mark Hill to our department. So, a few words of introduction. Professor Mark Hill is a giant in the computer architecture community. He obtained his PhD from the University of California at Berkeley, advised by the legendary Professor David Patterson. For those of you that are students in the audience here, you must have heard about the 3Cs model of the cache, compulsory, capacity, and conflict misses. That model owes its origins back to Professor Mark Hill's PhD dissertation. And if you want to write a thesis and aim to have impact, that's the kind of impact that you should aim to have, that finds its way to undergraduate textbooks. So this tradition of impact and excellence continued throughout Professor Mark Hill's career, which he started when he joined the faculty of the Department of Computer Sciences at the University of Wisconsin-Madison. His path-breaking contributions to computer architecture have repeatedly made their way to product impact, with his ideas finding their way to servers, laptops, and the phones that you use today. Indeed, there's a very large presence of our industry collaborators here in the audience today, and I'd like to welcome you all. So after a glorious career spanning 2 power 5 years at the University of Wisconsin, he retired as the Jean M. Amadal Professor, where he's now in emeritus status in 2020. His contributions have been recognized by a number of awards, most notably the 2019 Eckert Mauchly Award from the ACM. He's a fellow of the ACM, a fellow of the IEEE, and a fellow of the AAAS. He's also served in service roles for the computing community, where he served on the Computing Community Consortium, which is the CCC, from 2013 to 2021, including as its chair from 2018 to 2020. He also serves on the board of directors of the Computing Research Association, and he was the department chair of the the Department of Computer Science at the University of Wisconsin from 2014 to 17. Following his retirement from the University of Wisconsin, he was a partner hardware architect at Microsoft from 2020 to 2024, where he was on the Azure team. In addition, of course, to all of his research contributions, Professor Mark Hill is a legendary PhD advisor, having advised over 20 PhD students who have themselves gone to have distinguished careers in academia and industry. They have themselves gone on to win many awards, and the most recent such honor came just earlier this week, when his 2 power 4 student, which is our own Arkaprava Basu, won the highly prestigious Rashtriya Vigyan Yuva Puraskara. Where is he? This was formerly called the Shanti Swarum Bhatnagar Award, and it's the top award for young scientists in the country. Is he here? Yeah, he is. So he should be here. We just gave you a round of applause. You were not here. Okay, and finally, I just have one slide to share. Oh, yeah. Okay, so this is a special slide for Professor Mark Hill, who's had a really distinguished career for 32 years at the University of Wisconsin. And this web page here that I now maintain, it shows the history of the connection between our department here and the University of Wisconsin. Since its inception in 1969, our department has had the pleasure of having 11 Wisconsin alumni on its faculty. This is data that was originally gathered by our colleague Jayant Haritsa, but I now maintain this webpage. And when Arka joined us in 2018, there were 7 of us currently in the faculty. I believe that's the largest collection of Badger faculty anywhere worldwide. So even now we are 6 of us out of a faculty of 24. So let me conclude with a sincere word of thanks to all of our financial sponsors that have made this event possible today. In no particular order, they are Adobe, Nutanix, Google, Microsoft, AMD, and Mrs. Nirmala Govindan. Thank you very much for all of your generous contributions. So with that, let me warmly welcome Professor Mark Hill.
All right, we only have a mic here, huh? So I can't move.
No, there is a.
Is there a lapel mic?
Yeah.
Well, thank you for that very gracious introduction. Hope I can live up to the billing here. All right, how is the audio? All good in the back row? Now, by the way, a trick I learned is I put my abstract and bio in the first slide so that I can find it when I give a talk again. All right, so in computer architecture, we don't change the questions, we change the answers. And here's a picture of my lovely wife and I at doing some touristing in Bangalore, courtesy of ARCA. So, as you know, computer architecture is the big picture of computer hardware. And like all architects, we take components and build systems. And you know, building architects do this, but what computer architects do differently is that we do this recursively, from bottom up, gates to ALUs, blah, 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 all the way up to data centers. And I've been privileged for the last 4 years to be able to build systems where the system is the data center. And I used to use this picture with this absurd server replacing part of the data center to remind us that it was indeed a computer system with power and cooling and networking and compute. As all of you know, computing is a very complicated endeavor, and following the Roman dictum of divide and conquer, we have a computing stack ranging from problems and algorithms, applications, various levels of software, various levels of hardware. And one of the things that we're all guilty of is nicely depicted in this New Yorker cover, which shows the United States, but 3/5 of it is New York, and the rest is kind of small. And so this is what happens with our computing layers, is we operate in our layer and we think everyone else, yeah, they're kind of important, but you know, not that important. We don't really need to talk to them. But now we do have to talk to them, because as I'll show later, two-dimensional technology scaling, the conventional engine of Moore's law, has slowed dramatically. And so we're going to have to get some of our cost performance gains from crossing layers and doing optimizations. And this has to be done judiciously, because we can't expose everything, because that's too much complexity, which is the reason we created layers in the first place. Well, you might think these layers are just the subject of academia and how we structure our conferences, but I would argue they also are a strong force in the structure of companies. And so while the Moore's law was operating exceedingly effectively, the companies went into layers of applications, operating systems, microprocessors, etc. And this made sense because innovation was going forward so fast that you had relatively rigid boundaries between the layers, so it could go across companies, and then you had your plate full of doing innovation within your layer. This was not always the case, though. If you go earlier in the computing era, companies were vertically integrated because we were figuring out how to do computing at all. In fact, it wasn't until 1964 that IBM figured out how to do an instruction set architecture so that the same interface to software lasted more than one machine. So this required vertical integration in that era. What we're seeing now is a return to vertical integration. And I think part of the problem, or part of the force happening here, is that because Moore's law is slowing, we need to cross-layer innovation, so companies want to vertically integrate again. I have a picture there of a helix because I don't really think history repeats itself. It's not a circle, but certain aspects come back and other aspects are different. Not shown here, of course, is the new $5 trillion company, NVIDIA. We'll get back to that. All right, so when I was a new assistant professor, look at that, 37 years, no change. I asked a senior colleague, how do we update the questions on the computer architecture PhD qualifying exam? And my senior colleague, Jim Goodman, said, Mark, we don't change the questions, we change the answers. Was Jim Goodman still there when you were there, Arca? No, okay. Yeah, he was a great, he did early work on snooping cache coherence. So, of course, this was a joke, but there's a lot of truth to this. And I think to make it more accurate, it's really, in computer architecture, we mostly don't change the questions. It's the applications above us and the technology below us that change the answers. And then it's our job to recognize that change. So just as a concrete example of that, think about single instruction, multiple data, or SIMD. Those of you who have studied this was invented in the 1960s with machines like the Illinois IIISc 4. It was to the answer, how do you do compute? And it was the wrong answer. And then it became a niche answer with vector machines. And then with GPUs, it became a really important answer. So the question, how to do compute, didn't change, but the answer changed. And so what I'm going to do in this talk is look at some of these questions, but I'm not providing answers. I'm going to leave that as an exercise for the audience. Not today, it'll take you years, but I think there's many interesting things to do. So what are these eternal questions? The eternal questions are, how do best do these interacting factors of compute, memory, interconnect, storage, but I'm skipping it today because the talk is too long, security, power, cooling, and a bonus new question. As the talk has evolved, compute and memory have gotten longer and longer, so don't worry if I get to end of memory and it looks like I'm going to be talking for 2 hours. So with compute, as most of you know, the biggest trend is the trend for accelerators. Accelerator is a hardware component that executes a targeted computation class faster and usually with much less energy. The latter, less energy, is actually really important because computer systems are increasingly completely energy or power limited. And so doing things with less energy is important. And of course, everyone in the room is aware that deep learning is super important. And so the gorilla accelerator in the room is the GPU, such as from NVIDIA, TPUs from Google, and we even have a return to wafer scale integration, which I first saw in the 1980s, came back. I'm not sure it's the right answer now. It's kind of interesting to be, they're a startup that one of their non-good wafers is already in the Computer History Museum. So it's kind of an interesting thing. You know, usually it takes a while to become history, but they were history already. Key thing about accelerators is they require co-design. So I'll give you an example just with number representation. In deep learning, Google innovated with the bfloat 16, which used the same floating point exponent and sign size as FP32 that allowed easier conversion. But we want to use even fewer bits. And so what a number of machines have moved toward something called block floating point, which is actually invented many decades ago, where you make the mantisses smaller, but you really get savings by sharing the exponent with a block of numbers. In this case, we're sharing our 8-bit exponent with 16 mantisses. And if you do this, it doesn't work, right? To make it work, you have to do co-design, and you have to adjust your networks to make it happen. But once you've done that, you can make it work, and since the slide was done, people have pushed this even further to fewer and fewer bits, and we're going to see inference machines using I think single bit inference. By the way, with single bit multiplies are real easy. I can do it in one gate, maybe a NAND gate and an inverter, but logically an AND gate. So now I'm not saying that arithmetic design is the most important. I'm just giving an example of if these accelerators are really going to get the big savings, you need to do co-design. And this is a big shock because Intel, for example, had many decades of unbelievable success with an instruction set architecture that was relatively stable, and they didn't have to talk to the software people. They're still not good at talking to software people, and that's why they're in, one of the reasons why they're in deep doo-doo. All right, so most of my expertise is in general purpose, so the talk is a little biased for that, but let me say a little bit about AI, and I'll come back to something about memory systems later. I guess you don't really need me to tell you that generative AI is a big deal. But what I want to emphasize is everybody gets really excited about training. And training is like the supercomputing of AI, and it's super exciting. It has many challenges, but that's where the money is. That's not where the money is going to be made, and that's, I think, it's going to be a harder place to innovate. I think there's much more innovation possibilities in inference. And as a reminder, training is like going to college, and inference is like providing value in many different ways. Right now, AI it surprisingly for a new technology has a lot of return on investment already. Lots of times technologies, when they're introduced, they bust right away. Think self-driving cars. And it's doing pretty well because it makes tedious work faster, right? So it accelerates, for example, programming. It's not a fundamental change, it just makes programmers more productive. The pot of gold is when you make the near impossible practical. And I'll say a little bit about this in the next slide with the Gartner hype cycle. And so what are working opportunities? Well, obviously you can work on training, but I do think, and incremental training, but I do think inference is the place to be. And is inference going to happen in wearables, phone, laptop, edge, cloud? Yes. It's going to happen in all those places depending on the size of the question, the privacy requirements, the energy and communication. So there's a massive opportunity to study this. And also we have to remember the AI hardware and the general purpose. The software and hardware for AI and general purpose have to work together because all the value funnels through general purpose on the way out, unless, I guess, work continues on having GPUs do I/O. Another thing that's interesting that I saw at Microsoft is that deploying all these GPUs used a lot of power, and then so we had to be extra efficient on the general purpose side. So that's many opportunities there. And finally, you might think naively that if we make AI way more efficient, the inference and the training, that then we'll be able to get it done with less hardware. But this seems to obviously be in a place where Jevons paradox operates, which means that if you make it more efficient, you do so much more of it, you actually need more hardware and more power. And that's happening here. And that's because when you make it efficient enough, you make it cheap enough to apply it to more situations. So what's this Gartner hype cycle? This is a consulting firm that put a name on something that many people already know about. So we got, and you can barely see that, but this is time, I think it's 5 to 10 years, and this is expectations. And what Gartner observes, and they publish this all the time, is that most technologies go through a hype cycle where they go up and they're really hyped. And this generative AI, they put it at the top of the hype cycle on 2023, and then most fall into the trough of disillusionment, and then they either go nowhere or they come up. Okay, and the reason for this is actually human. And AI hasn't gone down this trough of disillusionment yet because I think the incremental fast gains, like for coding, have been super successful. But I predict with high probability there will be a bubble burst and the expectations will be met. And when this bubble bursts, well, maybe it's time to invest in companies because I do think AI is a really big deal. So as an example of this, when Steve Jobs introduced the iPhone, did any of you think, oh boy, that's going to be bad news for taxis? And that's because it took a while to figure out how to, the smartphone enabled Uber and Lyft and things like that, and it took a while to figure that out. But that's a profound shift, and that's the basic reason for the this hype curve. So what time am I supposed to finish by?
By 10:10.
10:10. Okay, I somehow set my timer wrong. Good. Because the timer was scary. All right, so the other thing that happens with these accelerators is people get really excited about writing a paper about an individual accelerator. And for GPUs, that's probably justified. But for many other systems, I think there's an untapped opportunity in dealing with multiple accelerators. Okay, so we already have examples of systems on a chip, or SoCs, that have multiple accelerators. In fact, this 2019 Apple chip has 42 accelerators where the only cores are shown in those two green rectangles. The rest are accelerators and caches. Now Apple has 1 billion customers, and so they can brute force the development of the hardware and the software. But if you want to apply many accelerators to applications, say a medical application that has 100,000 customers, then you have to figure out ways to do this much more efficiently. I believe using the CPUs as the control plane and the accelerators as the data plane. And there are many questions to do this in an elegant way. How do you program? How do you schedule? How do you communicate? How do you co-design? I mean, currently it's an absolute, I gotta be careful with my language here, absolute bad situation, because like each accelerator has its own software development kit and sometimes domain-specific language, and they connect in very ad hoc ways. So you systems people do better with this. And we have a paper calling on people to do better. Where are we going to put all these various accelerators, particularly in the general purpose world? So this is a simple taxonomy. I like taxonomies. And so on the x-axis is the cost of the accelerator, like how big it is from low to high. And on the y-axis is pervasiveness, like how many workloads could benefit from this. Okay, and so one set of accelerators, like the GPUs, they have a high cost and they're very, very good at what they do. They only do AI, so I'm giving them low pervasiveness. That's perhaps misleading if AI shows up in every workflow, but it's something to think about. And at the other extreme, we have a bunch of accelerators like data movement, verification, encryption, compression, which are already starting to move on the chips because they can be beneficial to almost all workloads. And you know, how do we coordinate all of these as shown in the previous slide? There is this sort of really difficult middle, which academics sometimes like to propose accelerators for. Like, you know, a B-tree accelerator, you know, that's bigger than a data mover accelerator, but it's limited to databases. So this is a hard place to go, and I'm going to skip the details of this in the interest of time. Traditionally, accelerators have either been sort of on, quote-unquote, the memory bus or on the I/O bus or PCIe. CXL is an interesting opportunity. It's physically like PCIe, but it lets you work more efficiently, so Compute Express Link. And so this is a slide from the CXL documentation. So we have a processor. It has this directly attached DDR memory. It's got the CXL bus lanes shown really big because it's from the CXL line. And you can connect to accelerators, an accelerator with some memory like HBM, or just memory. And you can do sort of coherent caching of this stuff, which is not common on PCIe. And so this is happening now, and in fact the greatest progress, as we'll show later, is in the type 3 or the third one where you're just connecting memory. Another opportunity which is also emerging is the fact that, as you may know, Moore's Law operated for a long time where we just could put more and more transistors on a chip of either the same size or we tended to do increasing size. And at some point this was not the right economic thing to do. It encountered yield problems, it encountered reticle problems, like the biggest thing you could fabricate in a system. And so companies have moved to chiplets. AMD was a big leader in this, Brian Black. And then you put these chiplets on a silicon interposer, and currently most of the signaling here is completely company proprietary. Now, I recognize this structure because it looks a lot like MSI logic. And some of you younger people don't even know what MSI is. That's medium scale integration. That was way before VLSI, very large scale integration. But we're going to see a return to this. This is kind of like that helix that I was talking about, where you have the ability to put multiple chiplets on the board, And with this emerging UCIe standard, Universal Chiplet Interconnect Express, you can even put chiplets in there that are designed by different companies. And so you could imagine, for example, somebody does a super duper node, and you want to have your own proprietary NIC to make it to work well in your cloud. You could put your chiplet on their board. And so I think it gives sort of many interesting design opportunities. Most of this stuff is two-dimensional, and two-dimensional scaling, as I forecasted before, is in deep trouble. Amazingly, this graph is from The Economist, and so what we have here is time on the x-axis, and we have log scale of the log scale on the y-axis, and the gray line shows node name. So that's what we name the technology. And we keep naming the technology as if it's getting way better. But the actual size, the gate transistor length, is shown in the red line. And so the node name is basically the marketing name, and the red one is the reality. So two-dimensional scaling is in trouble, and so we're going to move. Well, one of the ways to move is to 2.5D and 3D. What's 2.5D? 2.5D is basically a little 3D, right? That you maybe stack 2 chips or something like that. And 3D is the name given when you really go more serious. Now, what does 3D look like? Right now, we don't have any real good examples of 3D compute. It's happened first in memory, and there's a good reason for that. And so structurally, there's sort of 3 ways to do it. This is a model that oversimplifies. One is you take a bunch of 2D chips, you thin out a bunch of them, and then you stack them together. And this is exactly what happens for high bandwidth memory. And it's really expensive to do, and the connections between the chips are macroscopic through silicon vias. The next thing you can do is you can actually fabricate 3D monolithically in a process that basically repeats itself. So it's called decks, but you can think of it as floors of a skyscraper. You go through all the steps to make a device. That's the first floor, and then you repeat for floors. So the good news is that it's monolithic. The bad news is that the time it spends fabricating is proportional to these layers. And then what we really love is if we can do true 3D, where the circuit is actually operating 3-dimensionally. And we only have one commercially successful example of that, and that's NAND flash. And the question is, to what extent can we do this for logic? And we'll come back to that. For logic, it's going to require new cooling technologies. Okay, so by the way, with these things and other packaging innovations, I do think we have enough technological improvement that we can make our hardware continue to get better, not at the rate that we did when Moore's Law was in its heyday, but still pretty good. And so that's fun. Okay, so that's compute, but you'll notice compute was not necessarily that independent of other things. I dipped into a whole bunch of other things. Now we're going to go to memory, which is my bread and butter. Compute, I like to say, determines the peak performance of your computer system. It's memory that determines the sustained performance. All right, oversimplifying, you need the interconnect and storage too. And so what's happening with memory, and this is an old graph ending in 2018, but in the good old days, memory price per gigabyte was just heading down wonderfully. Then it stagnated for a while, and I don't have the newest data, but more recently, it's getting better really slowly, and its actual price is just determined by the balance of supply and demand, in a given year. So like in the pandemic, memory prices went, I guess, after the pandemic, memory prices started to go down, not shown here, when people had already bought all their new laptops. So why is this happening? Well, it's the poor 2D scaling. The technologists have not figured out how to make this the capacitor that's underneath the DRAM cell, scale super duper well, and have not been able to go 3D. I mean, they're 3D test chips, but they're just not economically viable. And so what this means is that if you want to directly attach DDR memory to your processor is getting better much faster than the DDR is getting better. And so you can't put enough memory directly attached to a processor chip to use the maximum number of cores. And so I think this is going to result in a forced response to two-tier memory. Now, nobody likes two-tier memory because it could be visible to software, and software changes we don't like. But remember, we had another forced change that affected software, and that was multi-core. Intel and other marketing, made you think that multi-core was this great innovation they thought the time was right for, but the time was right because they couldn't make the single-core processor faster and effectively use all the transistors. So it was the plan B, and so is two-tier memory. Okay, and so this works by using the CXL Type 3. So we have our Tier 1 memory, which is directly attached. All right, the laser pointer is gone. I did something wrong?
It's going dead. It's going dead.
Oh, I see. It's very light. Okay, and then we have our Tier 2 memory out here. And you can think of this as it's like zero-core NUMA. So the latency to the second memory is twice the DDR, or 3 times or 4 times in the early implementations. But there's no cores out there. And so you have to sort of manage it somehow. In fact, we named it ZNUMA for zero-core NUMA. NUMA stands for non-uniform memory architecture. So if you already have like a 2-socket system with one socket talks to the memory in the other system, it's of a similar latency. So how do you manage this? Essentially, there's 3 ways. There's something called Intel Flat Memory Mode, which I have a more detailed slide on, but I don't have time today, which essentially, especially if Tier 1 and Tier 2 are the same size, it treats the 2 levels as kind of like a direct map cache, where it can swap the lines, and it's completely automagic and transparent to software. Functionally, with a little bit of performance unpredictability that direct map caches have. The other thing you can do is you can say, well, especially in the cloud, we're running a lot of virtual machines, and so what we do is we profile the virtual machine and we find out whether the virtual machine is latency sensitive or not. If it's not latency sensitive, we put it all in level 2. If it is, we put at least the working set in level 1, and we still make it transparent to the application. And then finally, you can go application aware. This is not going to be practical for most applications, but for something super important like a database, which uses the really big machines, it can work. In part because a relational database has a large software data structure called a buffer pool, which is essentially a cache. And since it's a cache, you can make it a 2-level cache and do smart fetch and replacements. So those are the 3 things, and we already see this starting to happen. Further out is pooling and sharing. So support for coherent multi-socket systems is diminishing. So I think there's still support for 2-way, but not so much for more than that. And so for large analytic databases and applications that want to get really large, what do? Well, what you do is you have many sockets, the gray boxes, and they each have their level 1 memory, and then you somehow have enough interconnect so that the level 2 CXL memory is connected to all the sockets. And you can use this initially for something called pooling, where what pooling says is that any given region of the level 2 memory, such as 1 gigabyte, is allocated to at most one socket. So this basically appears to the socket like it has expandable memory of varying capacity depending on what fraction of level 2 it's assigned. But there's no sharing, which is good because then there's no coherence problem. Further out is to do sharing, and the real problem is that it's unlikely in the near future and arguably ever that we'll get full-blown hardware support for coherence at this level because the market doesn't seem to demand it. And so you'll have limited coherence, like 1% of your address space, and the rest has to be managed by software. And this can be handled for structured sharing where you use the smaller coherence space to do all your synchronization and coordination, and then you do essentially message passing efficiently via pointers to the level 2. And this is much a subject of research. There's a nice paper here from Emmett Witchell and others at the University of Texas called Tygon. All right, so the final thing I want to say about, no, it's not the final thing. The next thing I want to say is processing in memory. Okay, so processing in memory is an old idea. The picture that you can barely see is from 1995. People said, is this the correct way to do processing in memory in 1995? The answer was no. Is it the correct thing to do now? The answer may be yes. And the things that have changed is that conventional computing is not improving rapidly, so you need alternatives. There's some important apps like deep learning and recommendation systems that if this works for just those apps, it can be a valuable computer system. You don't have to make everything. And so it's now getting serious attention. So this paper shows a paper out of Samsung. However, there's two distinctions. One is processing in memory. So you're doing the processing actually on the DRAM chip. And the other is processing near memory, where you're doing processing in a logic die that's close in time. I actually am much more bullish on processing near memory because in memory, DRAM technology is just bad at processing. You get tremendous parallelism inside of the chip, but it's just not effective at it. And so I do think we're going to see processing in near memory, and there's a really obvious alternative, and this is happening already, so I'm not really predicting the future here, is that you have this HBM stack of DRAM, and beneath it, what we previously had was a logic die in an older process technology, because a logic die was only basically routing signals that came in from the SoC up and back. And so if we make this logic die be much closer to the current technology, maybe even the current technology, we can put processing down there. But what processing, right? You got a big challenge here. It's the good news is you're near a whole bunch of bandwidth. The bad news is that you have to sort of somehow program this, and if you put something too specific, it won't be applicable to enough applications. So there's research to be done there. Okay, I'm going to switch back to, I was doing a little thinking about AI inference, and I have 4 decades of memory hierarchy experience going back to the 3 C's, as graciously talked about. And so how does the memory hierarchy look different in GPUs? And so this is a simple model. So think of it like the 3C model. It's a good start. Don't take it too seriously. So for a lot of inference, the model, the LLM model fits in HBM. But the key value cache does not. Now, by the way, those of you in systems, if you think of a key value cache as having a key and a value, this is completely different. Think of it as, KV is nothing to do with that, because it turns out the key and the V are both matrices, and they're both of the same size, for example. So the indexing is done separately. So the key value cache does not. With something called page detention, which everybody does now, every time you fetch something from the KV cache, you fetch multiple megabytes. And so this is very different than getting 64 bytes. Your performance is really determined by the bandwidth. So how are we going to think about systems where the performance is determined by the bandwidth? let's do a simple model, kind of like Amdahl's law. Okay, so let's take a system where we're going to get some compute, and we got two memories, HBM and LPDDR, and they have bandwidths of 16 terabytes per second and 0.5 terabytes per second. And let's say, to simplify, that our workload is 100% bandwidth bound. So we want to manage this bandwidth. Our computation gets done completely hidden from the transfers. So if you want peak performance, how much of your data should you get from the LPDDR? %. Okay, so this graph shows x-axis what fraction you're getting from LPDDR, and on a y-axis normalized performance. And so the performance peaks at 3%. If you have to get 30% from LPDDR, if you have to get 10% from LPDDR, you're only getting a third of the performance. Why is this? It actually follows from some simple Amdahl's law-like kind of math. What we want for peak performance is for the transfers for a given phase from LPDR and HBM to end together. For them to, LPDR provides 3% of the bandwidth, so you want it to provide 3% of the data. Okay? And that's all well and good, but it may not be possible because that means that the HBM has to provide 97% of the data, and maybe its capacity is not big enough to hold what you need. Generalizing from this, what happens if you have n memory levels? And then secondly, what happens if you allow caching? So I had assumed before that both memories directly fed compute. Another model is the HBM, or the LPDR. You first transfer to the HBM, and then you do multiple transfers from the HBM. So we'll talk about those in the next slides. So in n levels, it turns out the math easily generalizes, and I hope to do a blog post on this soon. And what you want is memory-bound workloads maximize performance when they source data from each memory level proportional to its bandwidth. Now, a lot of hardware people see this and say, yeah, I know that. Now, were you thinking about that? That was a different question. But I really believe that software people don't know that. And so this says, for example, you can deploy a lot of that KV cache, and you can use a lot of capacity at low bandwidth memories, but on any given inference, you better not use very much of that capacity. And so I think that this is going to, we're going to have a renaissance on how to design memory hierarchies, because this is different than CPU memory hierarchies, which are more determined by latency than bandwidth, with the exception of high performance computing. All right, so what about caching? By the way, it's just work that hasn't been presented before, so you're getting brand new stuff. So for the extreme with caching, I'm just going to assume that you have to cache everything. So the LPDR, when you're going to use it, you're going to put it in HBM first, and then you're going to transfer it to compute. And obviously you could have a mix where some of it's cached and some of it goes direct, but the math's too hard for that. And so if you do this, the direct transfer, which we saw before, peaked at 3%. It turns out the caching thing looks kind of similar. It's a little different. You can barely see the difference here. In fact, it goes down the curve with the exact same math. Okay, so you might naively conclude caching doesn't work, which was my initial reaction. Then I thought about it. It actually does work. And the reason it works is that caching moves where you're operating on the x-axis. So let me explain that with an example. So let's say if you were doing it directly, you got 20% of your data from LPDR, then you'd be operating at this x-axis point, which is pathetic. Okay? If, on the other hand, you cache it and you reuse it 5 times, then you only have transferred it from the LPDR using 4% of its bandwidth, and so you're operating here. Okay, and so caching is important, and I think more work is needed to understand this more deeply. By the way, Arca, was that 10 after without questions or with questions?
It's Okay, you can go up to 10 after.
Okay. All right. But as predicted, by the way, don't be scared. These other things are not going to take as long. So next we're going to talk about interconnect and networking. I want to note that I already covered CXL and UCIe, which are interconnect. So what I'm going to do is just cover one more thing in this, and this is going to be done with this slide in the next slide, looking at the networks within the data center. Okay, and so what this figure from the Ultra Ethernet specification or paper shows is a bunch of nodes where node 2 is blown up. And so what's in a node is a CPU with some network interface cards or NICs, and then it has its accelerator. So XPU is a generalization of GPU. It could be your TPU or whatever. Okay, and these XPUs, they have their own local network. For NVIDIA GPUs, this local network is NVLink, so that's the purple network. Okay, then you have this blue network, which is sometimes called the back-end network, which is used within, just think of a distributed job to communicate among the nodes. This back-end network is particularly important for training, because training is a bulk synchronous thing where you compute and then you communicate a bunch and then you compute. And your performance is determined by the laggards. So if one node gets behind, there's essentially barrier synchronizations and everybody gets behind. So we want this back-end network to be good. And then the front-end network is the standard network for communicating among the nodes within the data center and to the whole world. Okay? And so one of the ways the back-end network has been improved is something called InfiniBand. InfiniBand is one of the few networks that has competed somewhat with Ethernet. But as Patterson joked in one of his books, you know, every edition had two networks, X and Ethernet. And then the next edition, the X network changed and Ethernet was still there. So I predict that Ethernet is here forever. No matter how much Ethernet changed, the network is going to be called Ethernet. So a consortium of companies decided to make Ethernet better, and I'm proud to say some of the people in my group helped make this happen, setting up the consortium and doing a lot of the technical work. And that's very proud, since I'm not a networking person, but I know enough to ask dumb questions, and so that helped. So the goal here is that we want to provide a high-performance, low-cost Ethernet-based solution, not InfiniBand, for AI workloads and, if we can, also high-performance computing. But AI is obviously the principal motivation. So you might think, well, come on, how can people improve on Ethernet that's been optimized for decades? Well, what we're going to do is we're going to change the problem. We're going to say, the first order, we only care about the back-end network. The back-end network has no transports that go across the world, and so we can make certain optimizations. So we're going to focus on workloads in the data center, and there's a bunch of changes, but the most important changes are to the transport layer. And by the way, do I have the reference to the paper? Oh, there it is. This is a really good paper. It's not the specification. Thorsten van Eycken wrote this paper, and it says why they made a bunch of choices. So if you're at all interested in networking, I recommend reading it. So what they did, and I don't have time to go all into this, is that they want to do connectionless packet delivery, so you don't have state proportional to the amount of, large state proportional to the number of connections. They do packet spraying, so to get a large block of data somewhere, you use multiple paths. When you use multiple paths, you can't really make them arrive in order, so you do some relaxed ordering. And especially for training, you have this, since we have this bulk synchronous where there's no communication and everybody blasts and there's no communication. Traditional TCP takes too long to respond, so we need a phase-aware congestion control that ramps up and quickly. There's also changes at lower levels, and this is really happening, and there's now many more companies, so I think it's super exciting. And you might say, you know, what really enabled this? What really enabled this is that network interface cards, or they're really chips now, they can be much smarter than they used to be. If you go back a decade or two, in the intervening time, compute has improved faster than the bandwidth. And so we can do more processing. This is an example where the technology that one is working with changed the capability, and so the answer, what we should do, should change. All right. So security. Well, security can be, multiple semester courses. So I'm going to touch on only one thing, which you may or may not be familiar with, which is called confidential compute. Currently, most cloud execution, we promise to protect your code and data from both external threats and our rogue employees. Now, since I'm a consultant for Microsoft, of course you would trust Microsoft, but what about the other guys? Well, more seriously, we want to move beyond a business promise to a cryptographic guarantee. And this is what confidential compute is about. And it's not a 0-1 thing. You're doing nothing and you're doing it perfectly. It's an incremental step. Despite the fact that marketing people will, of course, tell you that it's sort of all done. And it's very complicated to do it. And it's also really complicated to do it efficiently. Right? If you can do it, but you slow things down by a factor of 3, there's very few markets that want that. If you slow it by a factor of 20%, there's more that want it. You slow it by a factor of 1 or 2%, then everybody will take it because it's just more secure and it doesn't cost very much. And so I think this is it's an exciting new trend here. Why you need to care about this, even if you're not in security, is if you have this brilliant new idea that's not going to play well in a confidential compute future, your idea may not have that much of a future. So for example, if you think, well, what we need to do is in the network, we need to process some collectives that are doing some associative operation, fine, you can do that. But then you better think through how you can encrypt and decrypt and manage the keys, etc., in your network as well. Okay, so power, I'm going to skip wearables. Since I started this talk, I think people have become super aware of the data center power issues. One of the interesting things is that data centers are so big, they pay for fixed power. I want this many gigawatts or terawatts, and I'm going to pay for it, and if I use less, I still pay for it. So it doesn't help you to dynamically use less power. So you flip the problem on its head and you say, I want to use a constant amount of power as well as I can. And so you want to have various techniques where when load is high, maybe you can shed certain jobs, and when load is low, you can do some additional batch work. And these are the kinds of things that are happening, and you can see that link down there. Intermittent power is happening much more using green renewables. This problem actually is getting better. I should have put this graph in, but California now has a pretty large battery capacity, and so solar power can actually work at night as well. Of course, we have battery shortages as well. But I think there's a lot of domain for optimization, and power needs to be considered part of that data center computer system. And this problem is so bad, like Microsoft, for example, is investing in a fusion company and has contracted to restart the non-damaged fission reactor at 3 Mile Island. And so we're going to see a world where we're completely power limited for data centers. Even though they're still using, by the way, a small fraction of the world's power. I mean, just single-digit percents. But it's growing fast. Cooling, we've for most conventional computers, we've done air cooling, shown just on the left there. GPUs have already moved to cold plate, where you have these wires that move water very close to the chip and then come out, and then you blow air on it to get rid of the heat. This idea is going to go further, especially to enable 3D logic with something called microfluidics, which is essentially cold plate done at a much smaller level where you may even have channels running through the silicon stack. There's crazier ideas of actually immersing in various liquids, but those are currently on hold, in part because some of those liquids, which can't be water, that would short everything, have some environmental challenges. And you know, I think the real question for many architects and systems people is how do these things interact with the other questions? So if you can cool it really fast and you can use UCIe and you can make it really close, you know, you can logically reach more. And how does that change the right computer system? Okay, so I said the questions never changed, but that's a model and all models are wrong, some are useful. And so the new question is sustainability, which in the last year has just more and more people have become aware of it. I suppose you have too. How do we make things sustainable? Scope 1 is, you know, directly, bad stuff directly produced by you. Like for a data center, that's negligible unless you're running a diesel generator, but that's only in power failures. Scope 2 is the indirect energy, which is, you know, principally the energy to generate your power. So if your power is very green, good. If your power is very dirty, bad, as much of Taiwan's power is, where we get our chips. And then scope 3 is other emissions associated with your activities, and this is for data centers, it's principally the energy required to fabricate the chips. All the rest of the packaging, all the steel, all the concrete, it's in the round-off air. It's doing the chips. And so there's lots of interesting questions, in part because optimizing these scopes play off against each other. So for example, if we want to reduce scope 2, we might do 2 accelerators that are super good at what they do, using less power. But that takes more silicon area, which that's more scope 3. So there's a good opportunity for good work there. And that is my talk.
So, thanks a lot, Mark. I'm going to take over from Vinod since he had to step out shortly. So thanks for setting the lay of the land and set the trend for the entire systems workshop for the next couple of days. So we'll switch over to Q&A right now. Mark has been kind enough to stop well before his 10-10 mark. So we have time for questions. So if you raise your hand, we'll get a microphone over to you and you can ask away.
Then state your name and institution.
Yeah, so I'm Uday Pandula from IISc. So I'm trying to understand the two-tier memory architecture that you talked about. So does it add 2 levels of message passing? Because today we have, let's say we have GPUs, and if something doesn't fit, we just use multiple GPUs, training or inference, and so the software is layered on top of message passing. So we already have one level of message passing in that sense. So is the goal behind two-tier memory to provide more memory per node, and as a result add one more sort of a level of message passing which should make it harder to program? Or somehow is it can it be like transparent and just use the existing layer of message passing and perhaps not have an impact on the software? Yeah.
Okay, so the question is, you know, what's the impact of sort of two-tier memory on the software? In a general purpose node, it's not going to be message passing, but it's still going to be performance visible to the software. So if you have a 2-socket system, you have a bunch of CPUs, an SoC with a bunch of cores and some memory, and then the other one has some memory. And from this CPU accesses this memory, it's called that unit latency. When it accesses this other memory, call it twice the latency. CXL is going to act like that, except there's no cores over here. So some of the memory is going to be at a higher latency. So it is software visible in terms of performance. It won't be software visible in terms of correctness and message passing. How this is used in a GPU situation is to be done. It's not clear, I mean, CXL is based on PCIe, which doesn't have as much bandwidth as some of the GPU solutions want, and so it remains to be seen what's going to happen there. And by the way, the fact that CXL was based on CPU, the Devendra Sharma and others made a brilliant decision, because if it was something brand new, it couldn't have taken off. Because if you're a SoC vendor, you got PCIe lanes. It's one thing to make them also be able to do CXL. It's another thing to say, I'm going to have these new lanes that do only CXL, and if there's no CXL, they're totally wasted. People would have decided, well, I'll wait to see if CXL takes off, and then CXL can't take off because everybody was waiting. So it's a little non-optimal for AI, and we'll see what happens in that space. AI is now so powerful it might drive its own standard. And for that, it may be message passing. I don't know. But it's much easier to deal with in an AI situation.
Krishna?
Thank you for an excellent, thought-provoking talk. My name is Krishna Nandiwada from IIT Madras. I'll ask you a question to predict that will require predicting the future. See, from this time we have been studying, right? Like memory, okay, you have 1 level, 2 level, 3 level. It's keep on going. I mean, I have wondered sometime, will there come a time when people will say, okay, no, there won't be any hierarchy at all, or I mean, so will we reach a stage that there won't be any hierarchy, or will we keep on going with, I mean, n plus 1, n plus 2, and where will we stop?
Okay, so the question is, we keep seeing these number of memory levels increasing. Is there a way we can get rid of it, or is it going to keep going? Well, you know, the CXL I was talking about is 2 levels of taking 1 level memory and making it 2. But that's only part of the memory hierarchy. Like within the CPU SoC, there's multiple levels of caches, and then there's register file, and then behind that there might be some fast SSDs and there's some hard disks. So the memory hierarchy is really high. The idea of a memory hierarchy goes back to John von Neumann. And he says what we'd like to have is a really vast, super fast, memory. And, you sort of can't have that as long as there's finite fan-out. Right? If you can only branch out a little bit, if you're going to branch out to bigger and bigger and bigger, they're going to be further away and there's going to be more levels. And so I think as long as you have locality, you're going to have a memory hierarchy, because you can build something that creates the illusion of something better than you can physically build. And whether it's hidden to software, like caches are functionally hidden, or not, remains to be seen. In the general purpose world, mostly hidden. In the AI world, it's possible with co-design that you can make it very explicit. So I think it's sort of very exciting, but I think we're going to have many levels of memory. And the only question is, how do we manage it?
So we have an overflow room with a large number of students, and some of them have questions as well. So they'll be asking questions over Teams. They're right next door, but we'll do it over Teams. If you can unmute them, we'll just get them.
Can you unmute?
So those who are on Teams next door, can you just unmute yourself and ask away one question? Okay, while we're waiting for them, I'll come back to you. I know there's a raised hand over there. I come more from the top down, the runtime middleware layer, right? So what should we be doing? Hardware is moving so quickly. It's very hard to keep track, right? Is there some better way or we just leave it to the compilers and the sort of folks who sort of OS layer to deal with it? Or should we be doing something more proactive? Right?
So in which space, are you talking about the general purpose space? Or?
General purpose space, of course, AI, out of need, there is hardware, software, co-design. But beyond AI, right?
Yeah, and this space is a super active space. Like for example, people are programming, many things in Python, okay?
Yeah.
So, there's 2 definitions of efficiency, right? One is how efficiently does it execute, and the other is how efficient is it for somebody to write it. And many people are voting for that second efficiency, and so that gives plenty of opportunity for the runtime system. The question is, how much can you do statically?
Yeah.
you should do whatever you can statically, and you should do the rest dynamically, right? Because dynamic always has some overhead, but dynamic has, sort of more knowledge of what's really happening. So I don't have I think there's just sort of more opportunity. And some of this hardware, as it gets sort of more complicated, we don't want most programmers dealing with that complexity. So, the people who write the libraries, who write the middleware, are the ones that should deal with the complexity. I remember when multi-core first came out, I thought, well, maybe we should start teaching parallel programming to, early in our curriculum. And it turns out that was wrong, because most programmers still program sequentially, even though most cycles run in parallel. And it's because the cycles are programmed by these gurus. Mind me borrowing a term.
Okay, so it looks like it's going to sort of take a while to get them back. So there's one there, and then we'll end up with giant. So that's the reason.
Thanks, Mark, for an excellent talk. My name is Mohan Parthasarthi. I'm from Hewlett Packard Enterprise. I know you didn't want to talk too much about networking, but you talked about UEC. I see this alphabet soup of technologies coming up with UEC, UAL, SQE, eSUN, so many other things. So why do you think that's happening, and what do you think will happen in that space in terms of consolidation maybe?
Well, predictions are hard, especially of the future, about the future, is what Yogi Berra, baseball player, said. Yeah, there's an interesting fight going on, and it's less technology and it's more companies, right? I mean, AMD wants some certain things to happen, and Broadcom wants certain things to happen. And since it's a corporate thing, I'm less good at predicting sort of what's going to win out. Although I guess if I'm going to say anything, I wouldn't bet against Broadcom. And by the way, another open space is the sort of, NVIDIA has the NVLink for the purple. And, obviously we want to have some kind of answer to that in a more open space. And so that's where some of the alphabet soup is happening. And that'll depend on like the company winning and also the software being ready, right? Because this is software visible stuff. And so it's not like the old days where you're just, increasing the Ethernet bandwidth and, everybody else, all they had to say was, thank you very much.
Yeah. So, hi Mark, this is Bishwa from IIT Bombay. Great talk. So I just want to have your thoughts on designing high bandwidth cache hierarchy, especially for GPUs. So as you rightly said,
High bandwidth what?
cache hierarchy. And so as you rightly mentioned, we are kind of driven by latency and not bandwidth when we design the cache hierarchy. So are you seeing changes in technology similar to HBM, where you can bring something completely different and you create high bandwidth cache? Or you see microarchitectural changes providing that extra bandwidth that you need? Thanks.
Okay, so the question is, how much is the turn to bandwidth going to affect CPU memory hierarchies?
No, GPU.
GPU. Okay, yeah. So first of all, I don't think it's going to affect CPU memory hierarchies that much, because all those old things still happen. And by the way, CPUs are still important, right? I mean, all the interest is happening on GPUs, but you need this other stuff too. Well, this is where I wish I wasn't retired, right? Because I don't know exactly how this is going to play out, but it's really exciting to, after 4 decades, having some of the fundamentals change. And that simple model that I did is obviously oversimplified, but I don't have an answer. But it's an exercise for the audience.
I'm Jayant Haritsa from IISc. So Mark, a transformative idea in the 1980s was moving from the CISC to RISC, that is from complex instructions to reduced instructions. And Jim Goodman, whom you mentioned, used to talk a lot about it in the Sen 52 course. Now looking at the helix that you were predicting will happen and where ideas come around under new avatars, do you see the CISC instruction set coming back, especially because of the AI world, so that all our RISC processors will become CISC looking to the future?
Okay, so I'll paraphrase the question is, what about this risk debate that was very hot before many of you were born, or certainly aware of technology? It certainly is coming back. If you look at the TPU, for example, the TPU V1 has like a giant, its instruction set is very CISC-like. And it's because the trade-offs were completely different, and you could sort of send one instruction to the TPU, and it did a bunch of matrix multiplies, and so it absolutely has changed. And if you look at what NVIDIA's instructions are exceedingly complex, well, especially since they have a lot of data parallelism in them. A single instruction invokes a tremendous amount of work. And by the way, NVIDIA seems to be evolving its general purpose GPU architecture to being a domain-specific accelerator for machine learning with these tensor cores and these sort of new memory hierarchies. So I think there was a need for really simple instruction sets when chips were small in terms of number of transistors, and the compiler technology didn't do very well with complex instructions. And I think it's, all those things have changed for AI. On the CPU side, instruction sets are all about compatibility. And so x86 has one in certain domains. ARM only had a niche because it had a new business model. It had a business model where it could license you to do your own CPU. So it won not because, it didn't really win because of CIS versus RISC. It ran because of new business model. And so on the CPU side, the only new instruction set we're going to get is from the new business model. And that's RISC-V, which has much more freedom of what you can do with it than ARM does. And so I predict it's going to follow the same course that ARM did and become common. It already is being used quite a bit in non-user facing things, like a controller for something. And I think we're going to eventually see it used sort of more pervasively. But it's not for technical reasons, it's for business reasons.
Okay, so with that, we'll have to close the Q&A session in the interest of time. Thanks again, Mark, for So I will be moving around in the coffee break so they can catch you at that time and ask further questions.
Conference.
Yeah, wonderful. And a small token of appreciation from the department for your talk. Something to have your carry-on baggage.
Yeah. Well,
Thank you.
I fortunately had to bring a big dual stomp rocket to Argus Sun, so I have lots of baggage space. Remember to not walk away with the microphone. It's hot here somewhere.
Including Q&A. Sorry, didn't mean to. I'm sure though you could make use of that. Yeah, you're right. So, yes, 35. Yes. So we do have the next talk that's going to start. If you could get your seats, that'll be good. Okay, it's my great pleasure to introduce the next speaker for this morning session, our very own Professor Ramaswamy Govindarajan. All of us know him as Govind, who's a distinguished researcher and faculty at IISc. Govind's career spans over 4 decades, spanning computer architecture and high-performance computing. And he began his academic journey with a BSc in math from Madras University, followed by his bachelor's in electronics and communication and his PhD here at IISc. And following a detour for several years at various other universities and institutions as faculty and visiting faculty at Arizona State University, University of Delaware, Memorial University of Newfoundland, and McGill. he rejoined IISc and has since then been a cornerstone of our institution. He's been spearheading the Supercomputer Education and Research Center, where he served as a chair for over a decade. And he's also been a professor at the Department of Computer Science and Automation over here. Govind, among his many other accomplishments, is well known for being instrumental in spearheading the National Supercomputing Mission that is funded by the Government of India to the tune of over almost $700 million. And he's been sort of part of the journey right from the inception, crafting the vision document and serving on various technical committees, and finally seeing it a part of NSM fructify here within IISc. Right? He was also instrumental in commissioning the first petaflop supercomputer in India, right in the building next door at SCRC, the Sahastrat. Govind's research interest spans high-performance computing, architecture, compilation techniques, and many others. And he is not just published prolifically, but also him and his students have won many top awards, including at CGO and HIPC. And his students too have found the knack for excellence, and many of their doctoral theses have been recognized as well. Right? Govind himself has won many awards, including being a fellow of the Indian National Academy of Engineering, being an IEEE Computer Society Golden Core member, winning the Professor Rustom Choksi Award for Excellence in Research, and most recently in 2025 being recognized with the Dr. APJ Abdul Kalam HPC Lifetime Contribution Award. And this truly sort of honors him for helping shape the NSM mission from vision to execution. And when he's not architecting compilers or supercomputers, he's busy editing journals such as IEEE Micro, TACO, TOPC, and HPDC, JPDC, and also chairing various international conferences such as eScience, HPCA, and IPDPS, besides mentoring generations of HPC and architecture researchers. On a personal note, Govind was also chair of the SCRC when I was hired into the department. And the first thing I remember him saying, right, as chair, he sat me down on my first day and said, "Yogesh, you have a good volume of research, but if you're at IISc, quality matters, not quantity." And that's something that I've taken to heart in the last decade, and hopefully the results show for that. So with that, join me in welcoming Govind.
Thanks, Yogesh, for that very long introduction. Thank you so much. It's indeed an honor to talk right after Professor Mark Hill. As much as it is a privilege, it's also a very tough act to follow. Right? I hope that when you are reflecting on Mark's lecture, I would quickly sneak through my talk. First, let me thank Mark for pitching for inference, because that's exactly what I'm going to be talking about. We have seen that the hardware has evolved so much, starting from the simple single-core processor to processors that today have hundreds of cores in them. GPUs have taken center stage, both in general-purpose compute as well as in AI compute, and have advanced the compute capability significantly. Added to this list is the list of accelerators such as the tensor processing units and the neural processing units. And with these evolving computer architecture, we see that they have also kind of influenced and enhanced the size of the models in AI models, in deep neural networks and so on. And obviously, for several of the deep neural network frameworks, there have been compilers that have been built to translate these models, optimize these models to run in these different hardware architectures. Examples of these frameworks include things like TVM, XLA, and so on, and they specifically focus on deep neural networks. There are also similar efforts on the LLM side. I'm not going to touch upon that. But if you look at all of these things, what's really missing is support for classical ML models such as decision trees. And our work essentially addressed this particular component. Right? This is the work of my graduate student Ashwin Prasad, along with the collaborators from Microsoft Research and my colleague Uday from IISc. where we have actually developed a schedule-driven compiler framework for efficient execution of decision tree inferencing. Okay, before I get into the details of the talk, let me first quickly introduce what are decision trees. Right? Decision tree is basically a collection of, a decision tree example is basically a collection of trees where each tree has an internal node which does a quick comparison of one of the features of the input row along with, with a threshold value. The leaf node gives you a predicted value, and you basically collect these predicted values from different trees and you reduce them in some form to get the final prediction. Right? The reduction happens with the help of some reduction operations. I'll come back to this tree and then explain a little bit more about these predictions and the threshold values and how we use them. Okay, but before I get there, why do we concentrate on decision trees? Are they really important? Right? It turns out that several ML algorithms actually generate tree-based models. And surveys kind of say that tree-based models are still extremely popular because they are easy to explain. Right? For example, this survey which was done now 4 years ago, but when we started the work, that was actually the most recent survey, that kind of says that random forest and gradient boosting trees are two of the most popular ML models that people talk about. So that's the reason why we kind of focus on efficient execution or inferencing of decision trees, and they are used in a wide variety of applications such as finance, medicine, physics, and so on and so forth. Alright, so what does it mean to say walk the decision tree or make a prediction from a single decision tree? Right? As I mentioned earlier, the decision tree consists of internal nodes which essentially evaluates a predicate, and the leaf nodes which contain the value of the value. Okay? So for example, if you take the tree, it consists of a set of nodes, and we evaluate this tree or we walk this tree with an input feature vector. That input feature vector is something like this, and on each node we take one of these feature values. For example, in this case we take the first feature value and compare it with a threshold which is 0.5, and if the predicate evaluates to true, then you walk to the left, otherwise you walk to the right, and finally when you reach the leaf node, you say that based on this decision tree, right, for this input, the predicted value is 0.5. Now you collect these predicted values from all your trees, and then let's say you reduce it. For example, from these trees, if you have collected these prediction values, you could simply do a reduction of them and then say that the final prediction value for this is 2.7, and based on that you kind of do whatever you want. Okay, so this is exactly how the decision tree ensemble works. Okay, okay, so that's all fine, but if you want to execute these decision tree ensembles, what really happens in the hardware? How exactly are they getting executed? Right? So you call this routine called predict forest, and then the actual kernel, the code is not very easily visible here, but don't worry about it. I'll just walk you through this. Right? This is basically this is the standard inference kernel that we execute. And as you can see that here we are actually walking the decision, the set of decision trees for a set of inputs. Typically inferencing is done not on a single input row, but on a batch of inputs. So the top loop here is basically for a batch of inputs, and the inner loop here is for the different trees that are part of your mod. Right? And for each of these trees, you walk the tree using this while loop. And inside that while loop, what you do is that you find out what is this node supposed to do, which feature is it supposed to compare, and what is the threshold value. You compare that, and based on the comparison, you either go to the left or to the right. Okay, and you continue this until you go to the leaf node, and then you collect the predicted value, and then you accumulate the predicted value. It's all simple, right? But then there are several problems with this, and when you execute them on the CPUs or GPUs, you incur huge amounts of stalls. Why do these stalls occur? Right? For example, if you look at the access, this is an indirect access or irregular access. And such irregular accesses typically have very poor data locality. Not only that, based on that irregular access, you have a control dependence. And this is even worse, right? And you are going to have too much of control dependent stalls, and that's the second cause for concern. The third one is, of course, you walk the tree sequentially, right? That's the third problem. Although you have some amount of parallelism in terms of processing the different input rows and processing the different trees, right? You have these stalls that are going to really dominate. And unless you do this processing of these unless you do this processing, the parallel processing in correct way, you're going to actually not get good performance, and we will show that. Okay. So to summarize, in order to do decision tree inferencing, right, you need to walk an ensemble of trees, which are typically hundreds to thousands of trees, and you walk them for multiple inputs, which are typically in the order of thousands. But you incur a huge amount of core stalls due to irregular memory access, control dependence, and so on, and you don't exploit any vectorization because the tree walk is sequential, right? And there is not much spatial or temporal locality. Okay? You are unable to exploit vectorization. Naive parallelization might result in inefficiency and poor performance. And if you have to execute this on different target architecture, then you may want to do optimization specifically for each of these target architectures. So to address these problems, what we propose is that we propose this tree-beard compiler framework. But before we go to that, let's look at what is the state of the art, right? So typically decision tree inferencing is done with the help of efficient libraries, XGBoost, scikit-learn, and so on and so forth. And while these libraries are good in terms of giving you good performance, they are not optimized based on the model that you are executing or for the target architectures to a large extent. Okay? There are a couple of efforts which actually compile this decision tree inferencing, okay, and then generate code for the target architecture. One of them is Hummingbird, which basically generates a tensor code, but it has a large amount of redundant computations, and therefore it's not as efficient as what it should be. And the other one is Treelate, which generates a sequence of if-then-else code, and that suffers to a large extent due to the control dependence and so on. Okay, so we propose this tree-beard architecture, which is a layered compiler framework, which generates code for the decision trees, right, going through multiple levels of lowering or reducing the code from one form to the other. We call these things as high level, mid level, and low level things, generating code which can eventually be targeted for either your CPU architecture or for the GPU architectures. We go into some levels of details in here, right? So we use the MLIR compiler framework for doing this, and what we do is that we take the decision tree and perform some high-level optimization, right, at the high-level intermediate representation. And these includes optimizations which are based on, reordering the trees in the model, or padding the trees, or tiling the trees, and so on. At the mid-level, we generate code for these trees and reduce them in the form of for loops, as you can see here. And finally, at the low level, we generate vectorized code, as well as we do things like memory layout and so on. I'll go through some of these optimizations in the next few minutes. Okay? So at the high level, what we do is that we take the decision tree and we tile them in such a way so that we could do vectorization. This is an important optimization that we do specifically for CPUs. So let's say that we have a decision tree which is something like this, and the numbers here represent the probability of going to that particular leaf node for the input values, right? And as I mentioned earlier, if you execute this decision tree walk, you're going to walk one node at a time, which is sequential. So one way to tile this tree is to tile all these internal nodes together as a single tile and evaluate them in parallel. That's one way to tile them. And if you evaluate all of them in parallel, depending on the predicate values that you get for these three predicates, you can decide which way to go, right? So you can actually parallelize the predicate evaluation, and then in a single shot you can actually go to one of the leaf nodes. That's exactly what you can do. Let me take the example of tiling this using, let's say, up to 2 nodes in a tile. Then here is another way by which I can tile them, right? For example, I can tile these two nodes together and I can evaluate them in parallel, and depending on the value of these two predicates, either I'll have to go to this leftmost node or this node, or I have to go to another internal node where I do one more level of predicate evaluation. So in general, this is what we are going to do. Take the tree, tile them in some way so that the tiled part can be executed using vectorized instruction. That's the whole idea. Right? There are rules for doing valid tiling. I will not get into that. Okay, so this is one way of tiling the tree, and if you tile the tree this way, what is your estimated walk latency? Look at this, the estimated walk latency can be computed using simple math like this, right? But if you tile the loop alternatively in this way, where you put a parallelization on the path which is more likely to be traversed, then your estimated latency kind of reduces. So in your model, there could be trees which have this kind of property where certain walks are more probable, and therefore you need to optimize those walks as opposed to certain other walks. There could be trees where this may not necessarily be true, and all paths and all leaf nodes are equally probable, right? Therefore, your compiler now needs to look at this and then say that for this particular model, should I follow a simple tiling, or should I follow what is called the estimated walk latency and do the tile, right? And then walk through the path which is more likely to be taken. So our compiler can actually do this because the compiler now knows the model, it knows all the trees in the model, and it can tile it appropriately, right? And by tiling this, what we can do is, as I mentioned earlier, we are going to evaluate these two nodes together as a vectorized instruction. Okay, so that's the first step that we do in the high-level optimization, doing tree tiling. Then we also do something called tree reordering, which basically tries to put nodes which have equal number of steps to walk through together so that we can actually reduce the code that is generated for them, and we can do certain other optimizations as well. So this is a simple tree ordering that we do. And lastly, we also do some amount of padding. For example, if you note here, we have added this additional node here because we wanted every walk from this tree to have exactly two nodes to be evaluated and then one final prediction node. Because when you do that, you can actually generate code in a uniform way, which will reduce branching. And again, we do this because we want to reduce the amount of control dependence. Okay, at the mid-level, we take these reordered and padded trees and generate the loop nest for them. Okay, so structurally identical trees are traversed together, and we do that. And then within the loops, we can also do the typical loop optimizations like unrolling the loops and then doing interleaved walk of the trees and so on, so that when you do the interleaved walk of the tree, the dependencies can be pushed apart from each other, and therefore the dependent stalls that you incur can be masked by this interleaved walk. In the last step, we try to vectorize the code that we have identified as a tile. So for the nodes that are together as a tile, we now generate vectorized instructions, and as you can see that you collect all of these feature values together, you collect all of the threshold values together using vector instruction, and then you do a vector compare, and then you decide where to branch to. And to decide where to branch to, we use a lookup table, as you can see here. Depending on the results of the predicates that you have evaluated, this lookup table tells which path in the decision tree that you have to follow. So we optimize that as well using a simple lookup table. Okay. The last step is, of course, the results that you have got from these different decision trees have to be put together using an operation like reduction. And typically we talk about something like walking 100 trees or so on and so forth, and doing a reduction of these 100 values, unless you do it optimally, unless you do it efficiently, you are going to again get performance loss. The current support that we have for doing reduction in MLIR framework, right, is not sufficient, and if you do this reduction for arbitrary loop nest in an inefficient way, then you're going to cause too much of a performance degradation, right? So for this purpose, what we have done is that we have introduced an MLIR dialect called a reduce, and that dialect is actually optimized specifically for CPUs and specifically for GPUs separately, so that you generate efficient code for each one of them. in addition to those optimizations that I have already talked about, there are a whole bunch of other optimizations as well, such as in this particular example, I talk about the tree interleaving, where we walk the two trees together one after another, or the two trees in some parallel way. That kind of takes care of some of the stall. And here we talk about some kind of a memory layout of the tree so that I get better locality and so on. I'll not go into the details of that. Now let me spend the next 5 minutes talking about why our compiler is called schedule driven. Right? One of the aspects that we did not go into details is that when we walk multiple trees and for a batch of inputs, right, essentially we have a nested for loop. Right? Typically we have hundreds of these trees that we have to walk, and we have to process it for a batch of input, which is typically in the order of thousands. Right? And what this essentially means is that you need to walk each of these trees for each of those input rows. Right? And this is typically what is called as your iteration space. Okay? This iteration space can be executed in parallel, but again what we say is that you need to be cautious in terms of how you parallelize them, and we show that in the next few slides. Okay? Each one of these points is a point in the iteration space, and depending on how you walk this tree, right, you are going to exploit either parallelism in the input row or parallelism in doing the tree walks in parallel. Okay? So there is a lot of parallelism that is available here for sure, but if you throw all the parallelism on the system, you may not necessarily end up with an efficient execution. You may probably lose some performance there. And you want to make sure that in executing these things in parallel, right, where do you exploit data reuse in terms of, using the same model or the same tree, so to say, not the same model, but the same tree, or using the same input rows, because again remember, these input rows, right, could be, again hundreds of items in each feature. In each row there could be hundreds of features. Okay. What we have seen is that if you are not being careful in terms of scheduling your computations, in terms of doing what in parallel, then you might actually end up incurring up to 5x penalty in terms of performance. Okay, and therefore we kind of say that, look, let us try to specify what is a good schedule for a given model, and possibly identify this good schedule for each of the ML models that you are going to run and for the given target architecture. Okay, so let me just tell you the different kinds of schedules that you could possibly get for the iteration space that we discussed earlier. So here is the tiled walk of the iteration space, and when I say the tiled walk here, you can see that some of the trees are traversed, or at least one of the trees is traversed one after the other, and we try to do some amount of tree reuse there. And then after that, I go to the next tree and I walk down, right? And I kind of do this. So again, here what I do is that I use the same input across all of these trees. Sorry, I use the same tree but different inputs for each of the tree, right? And so on. So you can see here that there is a tree reuse. But if you walk the iteration space in the other way, then you will actually make use of reuse on the input data side. Okay, and here of course I have tiled it so that I am not walking, right, one tree for all the inputs, or all the trees for one input. I am not doing that. That's a possibility that you can also do it, right? State-of-the-art solution such as XGBoost, right, follows this particular schedule order, but its schedule order is fixed across all models and across all target architectures, right? Similarly, the rapid schedule from NVIDIA for GPU follows this particular fixed, right, schedule. Whereas what we say here is that the user can now specify the schedule, or the compiler can generate the schedule, right, based on some profile data and profile information, and identify the optimal schedule. In fact, our compiler framework generates this using a heuristic method. Okay, these are the constructs of the scheduling language. I will not go through them in detail, but what I will do is that I will take a simple example and then say what each of these constructs can possibly do. And in this example, so you can see this is how a schedule looks like, and by specifying reorder here, you will actually change the way in which things are walked. Instead of walking, right, for one input row across all the trees, you can now walk, right, one tree for the different input rows and so on. Okay, the command split here splits the walk into two parts. In terms of compiler terminology, this is what is called as a loop fission. You are separating these two things and then you do the walk. Okay, and then of course you can do the unroll walk, and then you can say that now trees of depth 2 or trees of depth 1, I want to unroll it to this level and so on. And you generate the code like this. So the compiler can now generate the code, and as I mentioned earlier, this is a schedule that the user can specify if the user knows for this model what works better. But if the user doesn't know this input but simply provides all of this information or simply provides these constructs or not even provide this construct, but if this framework is available for the compiler, then what the compiler can do is that it can generate some amount of profile information for the specific model that you are going to execute and for the target architecture and identify what is the right schedule for that. Okay? So that's exactly what our heuristic scheduler does. It explores a few possible schedules, and then from there it identifies what is the template schedule that will work better for this. Okay, so just to kind of explain this, for a single kernel or for a single model that we are talking about, right, if you say that what is its execution time across different schedules. So this particular model had about 5,000 plus schedules that are possible. The best schedule, of course, the normalized time is 1, and the worst schedule could be as low as 5 times, right? And a huge number of schedules fall in this small part, which is 1.0 to 1.1x or whatever. And as long as you can find something in this space, you are really good. So idea is that when you do this schedule exploration, how do you get these interesting schedules in as little a time as possible? Okay, so we have some heuristics which basically tries to get the schedule. I will not get into the details in the interest of time. Okay, so that's exactly what our compiler framework does, identifies these schedules and then generates codes for them. Okay, we evaluated it on a set of architectures. We evaluated it with both Intel and AMD processors. We evaluated it with NVIDIA GPUs as well as AMD MI GPUs, and we evaluated it on desktop processor versus server class processors and so on. And these are some of the models that we evaluated, and the number of trees in them, their depth, etc., are being given here. In addition to these trees to these models that we have evaluated, we have also evaluated about 700 synthetic models and evaluated our approach on that. Forgot to mention that all of these things were artifact evaluated both in micro as well as in SOSP. The code is available in open source if anybody is interested in using it. Okay, let me just quickly go through the performance numbers here. So the Treebird compiler, these are performance on the CPUs. Compared to naive execution, right, we achieve a speed up of 2.5 to 2 to 2.5x respectively on the Intel and AMD processors. As you can see here, these are the numbers, and the speed up numbers are with respect to the naive execution on the Intel and AMD processor. So there is no comparison between Intel and AMD processor here, but how much speed up do we get, and are we able to generate efficient code both for Intel and AMD processors? The answer is yes. When you and these are numbers on single core AMD processor and single core Intel processor. When you do this on multi-core AMD processors, we do get speed ups in the range of 10x to 15x for again AMD and Intel processors. As you can see here, they are able to exploit both vectorization as well as multi-cores effectively. Right? Compared to state-of-the-art executions on CPU, we see that we get a speed up of about 2.5x to 5x or 4x in this case. And the things that we have compared are the blue one is the XGBoost number, and the green one is Hummingbird, which is again a compiler generated code, and the red one is Treelight. And this is the speed up that is achieved by Treebird over each of these methods. So for example, I mentioned about the XGBoost approach. Over XGBoost, we get on an average about 2.5x speed up. Okay, and over Hummingbird and Tree Light, we get even higher speed up, even though they generate code. They are not generating code in the most efficient way. That's the reason. Okay. All right. Now let me also share some numbers on the GPUs. The compiler was able to generate code for the GPUs, and again you can see that the comparison here is over two state-of-the-art system, one called Rapids, which is developed by NVIDIA for the GPUs, and the other one is Taku, which is again a GPU compiler, and we achieve speedups in the range of 2 to 2.5. So you can see here, okay, 1.6x to 2.4x time speedup, and I have not shown XGBoost number here because compared to XGBoost, it's performing significantly faster, about 10x to 40x faster. That's why it is not shown in this graph. Let me quickly show you how our compiler performs for the synthetic loops that we have generated. So this says that for the various synthetic loops, right, what is the speed up that is being achieved by our compiler over Rapids. Lastly, this is about the heuristic scheduler that I talked about, right? What you need to see here is that this is the performance of the heuristic scheduler, how much is it off from the optimal schedule, okay? So you can see that it's at most about 0.05% off from, 5% off, I shouldn't say 0.05, 5% off from the optimal schedule, that is, it's at most 1.05x, so to say, and it achieves the schedule by exploring or spending time for less than 1% of the total execution time if you have to explore all the schedules. So that's exactly what it says, less than 5% degradation in about 1% of exhaustive exploration time. So that's exactly what Treebeard was able to do. Goes to my last slide. Okay. So to summarize, we need good compilers to generate code for efficient inferencing of decision trees, and Treebeard essentially solves this problem. These are schedule-driven code generation, and using the MLIR framework, it is retargetable because we generate LLVM-IR code, and from there we kind of target it towards individual target architecture, but we do these optimizations at multiple levels so that it generates this efficient code, and the framework is extensible in the sense that you can build on top of this. Okay, we are planning to exploit additional things like how do we use the statistics to optimize this ML executions and so on. We have also used the framework, and then based on this we could also build other frameworks for data analytics and so on. So that I will kind of close. Thank you very much.
Yeah, we'll have to contract the Q&A time because it's running slightly behind schedule. We have time for a few questions. Yes, please.
So if I understand correctly, by the way, very nice work. This is the kind of stuff we need. If I understand correctly, sometimes you're using dynamic information to drive your static optimizations, like the decision trees use some probabilities of what leaf you were likely to get. How stable is the past dynamic performance a good predictor of the future dynamic performance?
Okay, two things, right? One is the set of decision trees that we traverse is known a priori, so that we can optimize. The second thing is about the probabilities that you talk about, and these probabilities are typically based on your training data set, right? Based on your training data set, you know which part of the tree is going to be traversed how often. And this is unlikely to change in the sense that as long as your training is good and your input distribution follows the training distribution, it's likely to be the same, right? And therefore optimizing based on that is a reasonable assumption. But if it changes, then your model has to change, right? And you could use your dynamic inputs and then say that based on the last 100 inputs, this is exactly what I see, and I can go ahead and recompile it for that particular distribution. You can actually do that. Yeah, thank you.
Hello. So I am kind of interested in the vectorization part.
Indeed.
I am kind of interested in the vectorization part.
Okay.
So you have shown you have done the optimization on the IL level, but the benchmark only shows for the x86 machines. You have not at least not shown benchmarks for ARM machines. And I have also seen, so you are using some gather instructions they gather instructions, non-contiguous loads.
Okay.
That might have some impact on the performance.
Absolutely.
And neon, like as of the most of the ARM machines has neon support, they do not natively support gather tapping instructions.
Okay.
So is that a reason? That's why you have not shown the benchmarks for ARM.
All right. Okay. So let me address the question. First of all, the compiler is retargetable in the sense that we only generate the LLVM IR instructions, and from there you can generate the appropriate ARM vectorized instruction and so on. We didn't experiment with ARM at all, so we didn't have any idea how well it performs with the gather instructions or how well it doesn't perform with the gather instruction. We don't have. But yes, obviously, if you don't have support for gather itself is actually a time-consuming operation. If you don't have support for gather, it's going to be even worse, right? But again, you don't necessarily need to only rely on vectorization, right? If you have vectorization, yes, you can exploit it, and if you have good support for gather, you can exploit it. But again, remember that the way that you tile the tree, right, tells you that how much parallelism you want to exploit as opposed to how much redundant computations you want to incur. So that's a trade-off, right? You can always optimize on it.
One quick question in the back.
Hi, Professor Govind. This is Vedant from IIT Bombay. Very excellent talk. My question is, can your idea also be scalable to graph-based models like neural networks?
Okay, no, the quick answer is no, we haven't explored this at all, right? But for graph-based models which are more like graph neural networks, I really don't know whether these things will work. We need to think about it. Thank you.
Great. So let's thank Govind again. Small memento from the department.
Thank you. Thank you.
Yes.
I want the presenter's view.
All right. Welcome everyone to the first technical talk session. We have a session with 2 talks on ML and one talk on extracting parallelism. I'm Kanishka, I'm from AMD. It's my pleasure to host this session. The first speaker is Professor Murali Anavaram. He's chair professor in the ECE department at University of Southern California, and he also holds a joint position at the CS department at the same university. His main research interests are in security, privacy, and energy efficiency of computing systems. And he's going to talk to us about making ML affordable. He has a lot of accomplishments which I won't go through here. You can read his bio in the program. He's a Hall of Fame member in all the major conferences in our area, IISc, Micro, HPCA. He has a textbook that's widely used for computer architecture students. And he has a PhD from the University of Michigan, Ann Arbor.
Thank you for the introduction. It's my pleasure to talk a little bit about making ML affordable. And this work is sort of inspired by some of the, so my research group does a broad area of research topics. And for this particular workshop, I chose to present a very narrow slice of the work that we do in my group. And that's essentially looking at how do you make systems for machine learning more efficient. And it's not about improving the ML algorithms. That's not my wheelhouse. But we understand computing systems very well, and we are trying to exploit the existing computing system capabilities to make my machine learning models much more affordable. And so, but before I say anything else, first I need to give the credits to where it is due. These are my group of students and undergrads and grad students who work with me. And so much of what I present here is because of them. And of course also funded, much of my work is funded through a lot of industrial collaborations with Intel, Samsung, VMware, and so on and so forth. And for those of you who are from AMD, I'm looking for funding as well from AMD. All right, so let's take a look at what ML is. ML usage has a very broad spread currently. It has gone into, you can see, Google's and Microsoft's and Netflix and Amazon's. ML is everywhere. And the heart and soul of these machine learning systems is actually the cloud infrastructure, particularly in the form of data centers. And all of this began early in the form of DNNs, or basically what we call deep neural networks, such as ResNet models. And they needed nearly 1,000 petaflop second days in order to get them trained. And these are massive compute resource requirements that we never saw before, even in the supercomputing world. And then came the era of transformers. And that was just, DNN was just the beginning, and transformers really transformed the computing industry because they are trained with trillions of parameters on hundreds of trillions of tokens. And that means their compute demand is significantly more than anything humanity has ever seen. And if you look at the big distinction between where these models are and what the compute infrastructure has done is that till now we are always used to saying that Moore's law has been excellent, it gives us double the transistor density. But when it comes to machine learning, we look not so good. Because if you look at the model growth, which is shown on this graph here, and you look at the size, the performance of the GPUs, there's a substantial gap between the GPU's performance and the model's demands. So the model demands exceed the GPU's compute capability increases that has happened over time. And what does that mean?
it means a crushing cost of GPUs, because we have to now need what we could do on one GPU, the new models need 4 GPUs. What you could do on 4 GPUs, the new models need 100 GPUs. And as a result, the computing industry has been trying really hard to meet the demands of the machine learning models, and the cost of the GPUs has skyrocketed as a result. And in fact, much of the academic research is not able to actually do the research that is necessary for machine learning, simply because the cost of a GPU server is $100,000, and that's not chump change. And so it's a significant cost. So what do we need to do? Well, what we need to do is, number one, reduce the number of GPUs, reduce the number of GPUs, and reduce the number of GPUs. So this is really what we need to do in order to make machine learning affordable. That's the first of the tasks. So with respect to machine learning, there are two things that matter, right? One is throughput, how many tokens I can generate in LLMs on a second-by-second basis. That's what we call throughput. And the second one is the time to generate the tokens, the time between generation of tokens. How fast can we generate? These two things matter because the time to the number of tokens per second matter to the people who are actually running these servers. And time between tokens matters to the end user, because if I'm really slow in producing the tokens, then the user is not so keen on it. And so you need to optimize those two things. And I thought what we'll do is we did a lot of work on multiple dimensions of these two, but I'll just touch upon two specific things that we have done, one on the throughput side and one on the latency side, and we will go through them one at a time. So let's look at the first, improving the throughput of these systems, and how do we improve this throughput. So, but before I talk about it, I made the assumption that many of you may not necessarily know everything about LLMs. So I'm going to give you a little brief primer, 1 minute or 2 minute introduction to how LLMs work. LLMs are autoregressive generation processes. And what does that mean? What it means is that they predict the next word distribution in a sequence based on the preceding words that are generated from the prompt. And so this autoregressive property enables the models to generate one word at a time, conditioned on the context provided by the preceding word. So if I see a list of words, what's the next word? It depends on what I already seen. And then I take my existing word, add it to the current context, and then say what's the next word. So this is how autoregressive systems work. And so in the context of actual computational requirements for these systems, particularly using the transformer blocks, this is how the computational substrate looks like. Let's imagine for a moment that you have two tokens as a prompt, which we call x0 and x1, and we want to predict what the next token will be. Right? So this is basically what our task is. And how does it work? In the context of transformer blocks, basically you take these tokens, x0 and x1, and their embedding representations, and we transform them into Q, K, V matrices by multiplying them with these model parameters called the WQ, WK, and WV. And these are what is called the query vectors, the key vectors, and the value vectors. And so these are basically large matrices that are produced from this x0, x1. And then you take those values of queries and keys, and then you basically multiply it with the values to essentially get what is called the output activations. And basically this is telling you what is the most likely next word that I need, given that I already seen x0 and x1. And then once I know what the next word is, let's say the next word is going to be x2, I append that x2 to the x0, x1, and now this becomes my new prompt or the new context for the system. And now we go through the same process where we take this x0, x1, x2, multiply it with this WQ, WK, WV, and you get these QKV matrices. And then you do this attention score. I forgot to mention, attention is basically every word is looking at all the previous words and saying that which word really matters to me. Of the 5 words that are said before, what is the thing that really matters to me in order to decide what my next word should be? So roughly speaking, that's what attention is. And for those of you who are not in ML, just think of essentially I look at 10 words behind me and I say, oh, word 4 really matters to me most in order to decide what my next word should be. That's roughly speaking what we do. And so what is interesting to note in this whole computational framework is that you must have seen that much of this is recomputed again and again because x0 and x1 are already there, and you're essentially multiplying with WQ, WK, WV, and the attention scores are also reproduced again. And hence, this process is this in autoregressive manner. If you're doing 10,000 tokens as an output, you are producing this 10,000 times repeated computations again and again and again. And that's a very expensive process to do because all of these are large matrices in the orders of hundreds of millions, if not billions of parameters for each layer. And there are dozens of such layers to compute on. And so this is a very, very expensive process. And so obviously, people have recognized this problem, and they said, well, why are we recomputing them when we can store them, right? So we can basically, the standard process is caching. So you can take the key, the K matrices and the V matrices that we generated, and then we basically cache them. And we basically, when you cache them, you only need to recompute just the new token that is coming in. So when the X2 walks in, it only needs to compute the new attention score, that is the last row of the matrix that I just described, and it only needs to compute one row of K and one row of V, and hence we reuse the computation essentially by caching these systems. But what did we do in the process? We took the computational problem and transformed that into a huge memory problem. Right, like we basically now have to store this data instead of recomputing this system, these values, and so this has essentially caused. So the KV cache reduces computation capacities but grows linearly. And now, if you look at the throughput, and this is what I'm talking about, number of tokens generated per second, the throughput is generally proportional to the batch size. If I can take every one of your queries and then I can simultaneously process them, I get a better throughput than if I just took Shweta's query and only started with her query and produces words for that query. And so I want to increase my batch size, but the fundamental problem with batch size increasing is that the KV cache becomes extraordinarily large because it's basically proportional to the number prompt, which is the number of elements in the batch that you have. And so ideally I would like really, really large batches, but then if you look at GPUs, even the best of the GPUs have maybe around 80 gigabytes of HBM, and therefore you are kind of limited by what that KV cache storage is going to look like. And therefore the memory system really hobbles your ability to produce large throughput improvements in these systems. And so, and as Mark mentioned, we can look at alternative strategies. And as coming from computer systems design perspective, we look at CPUs and say, hey, CPUs has huge amounts of DRAM, relatively cheap. Why don't we just store the KV caches on the CPU DRAMs and allow the GPU to not be overloaded in terms of its KV cache storage requirements? And so the offloading system is relatively simple conceptually. We basically put the KV caches on the CPU's DRAM, let's say it's at 512 gigabytes, and then use a PCIe Express to transfer the KV cache to the GPU HBM and allow the GPUs to run as required. This allows us to increase the batch size dramatically, increase the throughput, except there's a problem. And the problem is the following, that PCIe is not the fastest thing on the planet today. It's very slow relative to the rest of the networking connections. And as a result, when you start transferring these KV caches to the GPU in order to compute the next token, the GPU is just spinning idling, right? And when it is spinning and idling, you're wasting a $100,000 resource. And that's not great, right? Like you want to be able to use the GPU to every single cycle that's actually available to you. And so we wanted to, so this caching process is relatively ineffective. And it turns out that when we implemented this very simple principle by using this notion of caching and just by basically offloading it, it did not work because the computational, the transmission delay on the PCIe Express is significantly larger than the savings that you could otherwise get, and hence we didn't get a whole lot of improvement. And so that basically led us to think about what can we do. And here is the key observation. If the whole talk, this is the one slide, and there are two slides on the key novelty, and this is the novelty of this idea. The idea is that if you look at the activations, which are basically my X0, X1, X2 tokens, and if you look at the KV caches, what do you see? If WQ, WK, and WV are all the matrices, K and V values are twice the size of activations. right? Like basically for every x0, I have a k and I have a v. So I've doubled the size of the memory that is actually stored in the kv caches. And therefore, if I actually decided not to kv cache and instead want to recompute and put these activations on the CPU's DRAM, I can recompute, but I only need to transfer half of the data because I don't need to transfer k and v. Instead, I only need to transfer just the activations. So that seems like a reasonable choice, but that means we are now putting a lot of load on the GPU to recompute now, and that's not also a great solution, and that led to this complicated trade-off on how we can solve this problem. So the problem, therefore, the solution that we propose is actually interesting and simple, which is this: to take the KV cache, chunk it into smaller pieces. Let's show next this piece 1, piece 2, piece 3. And these gray pieces that are shown in this picture are not transmitted to the GPU, but instead we tell the GPU that I'm transmitting a KV cache 1, but I want you to recompute this missing piece for yourself. So think of this as a whole block that are missing pieces. It's the responsibility of the GPU to compute the missing pieces while the remaining pieces are being transmitted by the PCIe from the CPU side. So if you do that, we now allow partial recomputation on this GPU and partial transmission of the data from the CPU to the GPU so as to maximally utilize the available PCIe bandwidth and overlap the entire bandwidth of transmission time to recompute on the GPU because you're using only half the bandwidth availability. And that is exactly what the KVPR solution does, which is basically partial recomputation of the KV values, and you transmit you transmit the XIs, and those XIs are being computed by the GPU to produce the KV values. Simultaneously, you transmit a chunk of the KV cache directly, and now you stitch them together back on the GPU side to create your entire KV cache for your computational requirements. And this is the system that we built, and you can download this and run it. And this allows us to improve the decode throughput by 46%, right? And that means we can reduce the cost of our GPUs from $100,000 to $60,000, which is a significant reduction in the total cost of the system in terms of the overall implementation efficiency. And so this is a 46% improvement in the throughput tokens per second, and we run it on very many models and things like that. I just want to show you one result. Results are not so interesting as much as the idea itself, but the key idea is, I think, what we just discussed. So that is one way of thinking about throughput improvements. So basically, the throughput improvements come from me leaning on the CPU and saying that, hey, CPU, you're already there, your memory is cheap, why don't you help me as a very expensive GPU resource to sort of cooperatively execute between the CPU and GPU. And we have done other works for those students who are interested in. You can look up something called CDLRM, which is a recommendation model where CPUs and GPUs collaboratively work to improve the system performance for recommendation models as well. It's a different idea, but similar and conceptually similar in terms of allowing CPU to help the GPUs. So that was basically what KVPR does. And what do we do next? Well, we still need to improve the GPU usage, basically reduce the number of GPUs. But now I want to turn my attention from reducing improving the throughput to reducing the latency. Now this is on the other side, the user side. How do I make users happy by giving them tokens faster than otherwise done? So in order to understand what is done today to improve the token production speed, you should understand a little bit about what is called the speculative decoding. Speculative decoding is the idea that, imagine that we have a big giant model, and imagine that there's a tiny model. The tiny model is predicting words very, very fast, but it may not be very accurate. But you assume that the words produced by the tiny model are good enough, and you feed it to the large model, and the large model will use these predicted tokens and picks off, this is a good token, if I generated it, I would have generated the exact same one. And I take a second token, I say, this is what's produced by the small model. If the small model produced a token and the big model produced exactly the same token, we took off and said that is a good token. But occasionally they diverge. Because speculation, the small model may produce something that the big model says, no, that's not what I would have produced. But where is the performance benefit comes from? The performance benefit comes from the fact that you can do a much faster verification than generation of the tokens. That's basically the principle. And let me kind of give you a very brief overview of how that actually works. And I'm going to use, and there are different ways of doing speculative decoding. This is called speculative decoding. Different ways. One is to create separate model, one big model, one small model. But the one which I'm going to use is what's called layer skip, which is a mechanism that published by Meta, and the way it works is as follows. So if you take a prefix, which is your original prompt, and you skip, we just use only layer 2, and then you skip over the remaining layers of the primary model itself. And then you produce a token x1, then you use that as an addition to the prefix, and then you do the same thing. You run to the first 2 layers, skip over the remaining layers, produce x2, and then you do this process repeatedly to produce basically what we call a set of tokens. In this case, it is producing a total of 4 tokens. And this is what we call a round of prediction. So in a single round, we produce 4 tokens as speculation. And now it's the responsibility of the bigger model to come into play and say, hey, you gave me 4 tokens really fast. Let me actually verify them. And the verification process is highly parallel, as opposed to sequentially decoding token after token after token. Since we already have 4 tokens, let's verify all 4 of them are correct or not. And this is where the distinction comes in, because speculative decoding is really fast because you can do this verification parallelly. And so the verification process is simply the following. You take all the 4 tokens, you send them through all the layers that are not yet touched. In this case, layer 2 and layer 1 are skipped because we already did this with a smaller model. And then we go through layer 3, layer 4, and then the head layer. And then we say that this is what I produced. This is the bigger model would have produced this information. And we say that you and I disagree. The speculation, the small model, and the big model disagree on the 4th token that is produced, but the remaining tokens, I agree with you. And therefore, now we generated suddenly 3 tokens very fast, and then on the 4th token, you actually did not generate the right token. And therefore, what do? We go back to this x1, x2, x3, and accept that to be my prefix, and next time I'm going to use prefix plus x1 plus x2 plus x3, and then start the model again. And that's basically the second round begins in that process. So basically, when I say the word round means a set of tokens produced by the speculation engine, and then a verification that is actually done parallelly on all of these tokens, and then decide which of those tokens have succeeded, and then we start the process all over again. So this is basically what we call a round, and this is goes through produce, verify cycles, and that's the round definition in our system. So this is what is called layer skip, and this is what is done. And what we noticed is that there are 2 key observations. Layer skip speed up relies on the exit layer and speculation length. That should be obvious to you, right? If I skip over in layer 1 and then get all the way to the LM head, I would be very fast. But the probability that I'm making a mistake is going to be higher because I'm using lesser information, right? But if I ran through layer 1, layer 2, layer 3, and then I skipped over layer 4, I didn't get a lot of speed up because my small model is just as big as the big model, maybe slightly smaller. And so there's this trade-off between how deep I want to go to speculate, and then in the process become very slow, or how quickly I generate the token, but in the process become less accurate. So there is that trade-off that one has to deal with. And layer skip uses a very rigid, fixed layer skip model. And we said the optimal exit layer should be dependent on the task and the context. And therefore, we have to figure out how to decide, oh, for this particular question that you're posing, this is a difficult question. I need more layers to actually give you a confident answer. For this question that you are posing, which is a relatively simple question, I will give you a shorter number of layers I'm going to compute on and skip many, many layers. And that's what I want to do dynamically back and forth between these systems. And so, with that said, how do we dynamically skip? What's the controlling mechanism that allows us to do the skipping mechanism? And the way to do that is what is called TPL. This is called the token per layer metric that this particular work proposes. And this is a very simple, I know no math, and that's why it's going to be very simple mathematics. And the basic principle is that the TPL is defined by number of tokens that are eventually generated. So if I produced 50 tokens but I accepted only 35, that will be the 35 tokens, divided by the number of layers that I actually loaded in order to speculatively generate the token. So you can see this is actually playing with the trade-off nicely, that if I loaded the layers a lot, I get a better generated tokens, but then this is the denominator, it weighs down my TPL. But if the number of loaded layers is fewer, but the number of generated tokens is also smaller, it also weighs down. So you have this nice trade-off that we can actually balance with. And so the TPL is defined by this metric alpha. Alpha is just the acceptance rate. The acceptance rate is simply saying that if I use one layer, how much would have been my acceptance rate? If I use 2 layers, what would be my acceptance rate? If I use 3 layers, what would be acceptance rate? And that's what this is defined by alpha L, where L is the layer number, 1, 2, 3, 4, and so on and so forth. So this is all great, except I don't know how to produce these alpha values. I need to know what would be the prediction of the tokens if I have 1 or 2 or 3 or so on and so forth. And so this is where the little bit of the innovation in terms of my knowledge of microarchitecture comes into play. We use past to predict what the future would look like. And the basic principle is that to estimate the TPL, Dell requires the token acceptance rate possibilities. And this is where Dell uses what's called shadow tokens. And so this is really interesting in the sense that, remember, if I produce 4 tokens, I have to eventually verify them, right? And in the verification process, I let these 4 tokens go through layer 1, layer 2, 3, 4, all the layers. And therefore, I have already computed the intermediate activations for all the layers in the system. It's not just one layer, but all the layers in the system. And therefore, I cannot pretend. And what am I pretending about? I'm pretending that, hey, if I actually use not layer 2 but layer 3, I would have produced additional 1 or 2 good tokens. If I pretended to use layer 4, I would have produced an additional number of tokens. And so, during the verification process, I am going to simultaneously compute if I use not layer 2, layer 3, what would have been the acceptance rate? If I use layer 4, what would have been the acceptance rate, and so on and so forth. And therefore, we can do a very simple, what is called a shadow token generation process, where during the verification process, we said, oh, we got this x1, x2, x3, x4, but let's actually, by using layer 2, but let me ask the question, what happens if I only use layer 1? I can actually compute that because the verification already gave me that information. It's a very small additional computation that I have to do that what if conditions, right? It is basically saying, what if I have used layer 1? What if I have used layer 3? What if I have used layer 4? So I can do this what if conditions for every layer, and using that what if condition, we can now estimate what the accuracy is if I use layer 1 or layer 2 or layer 3 or layer 4 and so on and so forth. And that allows the system to basically produce an expected acceptance rate alpha L, which is denoted by a weighted sum of the number of correct tokens that I actually predicted. The math again is not complicated, it's a simple one, but it allows you to, and it uses a exponential decay function, which means that if I was wrong a long time ago, I can give it less weight, but more recent history matters more than a long time history ago, right? And so that's the basic idea, is that you allow the system to automatically adjust and say that long history, less important, recent history, more important, and that's what this weighted summation actually allows us to do with an exponential decay function. And we can implement this relatively straightforward. And again, in most of my talks, I don't present any results because I don't think it's very interesting, but basically it will achieve around 2.5x improvement over autoregressive decoding across different tasks and different models, basically allowing us to show that this approach substantially improves your overall token speed, therefore making your customers, whether they are the AMD customers or the Nutanix customers, to make you feel like you are producing results to them much faster than otherwise be. And this is also important for reducing my number 1 goal, which is GPUs, right? Because if I produce faster, then I can serve more users to come into the system, and I don't have to need an additional GPU in the system itself. So that's the experiment, and then basically this is a plug-and-play module for Layerscape, and it is very easy to implement. It's very lightweight design mechanism, because we add a little bit of cost. Remember that the shorter tokens cost a little bit of extra computation, but it's substantially small. It's not that big a deal. We implemented it, we evaluated it, and updated COLM conference and language models this year, for those of you who are more interested in understanding the details of the paper itself. And so, with that, I will stop and let you folks ask me any questions you have.
So there's multiple people working on ML inferencing, so there'll be questions. Let's go there first.
From Microsoft Research. Interesting talk, but basic question, how do you deal with the stochasticity of the underlying process? Like when you do verification, even if you run the same LLM machinery the second time, it cannot produce the same token. So how do you do your verification given that?
Let me phrase. Remember that for the same input activations, there is no stochasticity. The stochasticity comes from the fact that the token that is generated, which is appended, causes the stochasticity for what the next token would be. But if I give you a set of x1 and x2 and you start with the same initial state, there is no stochasticity in itself, because unless there is a stochasticity in the output probability, like when you do a softmax and then you use some stochasticity, right? But that's not a problem for us. That's just a standard stochasticity problem that exists even without the speculation that we discussed in this approach. And so we assume that that's acceptable, right? When I ask the same question twice and I choose a slightly different probability number, that's okay for us.
I'm Anusha from AMD, not from the GPU side. Yeah, so I have a question. The first part of the talk, you said that there's a partial transfer and then partial computation right in the GPU versus the GPU being idle. So what's the trade-off here? Like either your GPU is idle or you're doing GPU partial computation, right? So I didn't get the data. Did you compare with that baseline as well?
Yeah, so the big trade-off is that when the GPU is idle, your transfer time has grown. So your GPU's idleness is extended for a long period of time. So for example, just to put an idea, let's say that the GPU is idle for 100 milliseconds. What we are saying is that in that 100 milliseconds, let it do partial computation. Let's say it will do 50 milliseconds of computation. And then I only transfer part of the data in that 50 milliseconds of computation. And if in a perfect world, I would be able to take whatever the transmission costs and perfectly overlap with the GPU's computational fabric, and we can basically shrink the overall latency in that system.
In the CPU world, we have this concept of prefetching. Is that there in
Excellent question. I expected this question, and I just talked to my student yesterday night on this one. So the prefetching basically means that I can move the data before I need it. The assumption is that the prefetching data has space in the GPU's HBM to load that data. And the fundamental problem is we are running at HBM's max capacity. And if you want to prefetch, you have to basically double buffer, which means your HBM capacity shrinks because half of the space, in the worst case, is for the prefetched data so that you can prefetch before it is needed, but that means the branch size shrinks as well. So unlike the CPU prefetching scenarios, here we are really max capacity at this point in time, and therefore there's no space for like randomly bringing things when ahead of time, which means something else needs to leave, and that's not great. I'm happy to talk.
We just need one more question, maybe from back.
Hi, I'm Shrikul from Google, and had a question about, you mentioned this helps in the decode, right? So what about the prefill part? Does your approach with the partial helps in prefill as well? Because that's more compute bound, right?
When you say partial, as in which one are we talking about?
KVPR part. Right, so
so in our particular scenario, we are only interested in the decode latency because the prefills are done. We assume that the prefill already exists in the system. But prefilling itself is mostly compute bound, right? It's not as much on the memory side of things, and therefore it's not necessary that you have to use CPU DRAM to do the prefill process. You can just use the HBM because you're mostly GPU computational cycle bound at that point.
All right, so we'll have to stop it there. Next talk, we'll start with the remote room first, because we didn't get to do it this time. So let's thank the speaker. Thank you for your questions.
Thank you.
So our next speaker is Saurabh Goyal. Saurabh Goyal is a senior principal and researcher at Microsoft Research. He works on ML efficiency, ML inferencing efficiency. He spent many years at Google before that, working on search infrastructure and Google Assistant. So, whenever you're ready.
I have a couple of
Thank you, Kanishka. I'm Saurabh. As Kanishka mentioned, I work at Microsoft Research. I work in the systems group in Microsoft Research, and we have a very large contingent here. So, if you want to talk to anyone, please feel free to catch us at lunch. Lately, most of the systems group has been working on problems related to LLM efficiency, and one such work stream that I've been working on is what I'll present. It's around sparse attention techniques, which is used to optimize the attention operation in LLM inference. I'll mostly be presenting an overview of sparse attention. Is it good, Mike? Borrowing from works from other people as well, but also some case studies of things that we've done. So Murli has covered some of this, but I want to highlight that in a LLM inference, typically there are n transformer blocks that every token will go through, and there are two primary operations in those transformer blocks, and all these operations are primarily large matrix multiplications from a performance point of view. For the feed forward operation, the feed forward operation, the incoming vector is multiplied by weight matrices, and it's independent for every token. Whereas for the self-attention operation, which is sometimes called the token mixing operation, the weight vector, the incoming vector is multiplied by a matrix that's composed of vectors from all the past tokens intermediate outputs. So it's also something that Murli had talked about, but I just want to go a little more detail into what the self-attention operation is. So if these are the three tokens, this is the incoming vector. You first project that into query, key, and value vectors for each of the tokens. This is the key value that Mark was talking about, not the database key value. But these are the three vectors that every token will produce. And then the query of, let's say, the last token is multiplied by the key of each of the past tokens to produce a weight vector. So if you look inside this box, Q3 is multiplied by K1, by K2, and K3 to produce a scalar weight for each of these tokens. That weight is then normalized using a softmax operation. And then using those weights, you compute a weighted average of the values of all the past tokens. And that now is your representation of this incoming vector. Okay, so there are two observations that we'll make here, which we'll utilize. One is that each token is attending to every other token in the past. So you can imagine what will happen with this is, as the sequence lengths grow longer and longer, this doesn't scale very well. It ends up being quadratic in the sequence length. So even if your GPUs become 2x faster, the memory bandwidths become 2x faster, you'll end up not being able to serve a sequence length which is 2x longer. So that's one observation. The second is that there is a softmax operation here, and its effect here is that it ends up making this weight vector sparse. And most of the values become close to 0. So what that means is, even if you're attending to all the tokens, you're doing the work to attend to all the tokens, but most of the time that value is 0. So only a few of those tokens are important. And we utilize this observation when we design schemes to improve attention. Now, why is this important? Long sequences are becoming increasingly important in LLM inference. We all know about these O1, O3 kind of models, DeepSeek R1 models, which are now targeting reasoning workloads, where in order to answer a question, you first generate a long chain of thought reasoning before you can come up with an answer. Then there are also traditional workloads for LLM, not very old, where to answer a question, you first retrieve a bunch of documents from a corpus, and then use those documents along with the question and feed that to the LLM to generate an answer. So again, here, typically the input is very long, whereas in the reasoning workloads, it's the output that is particularly long. And then there are other workloads like multimodal, where you feed in videos or images, or code nowadays. We are doing repository level coding using LLM. So long sequences are just becoming more and more popular. And attention is a bottleneck there, so we need to figure out how to improve attention. So in this talk, I'll cover a class of techniques which is called sparse attention, and here you will be attending not to all the tokens but to a subset of tokens. And there are few subclasses that we can divide these approaches into. One is called fixed sparsity patterns. The second is using a pattern that is aware of the workload that we are processing. And a third is a completely dynamic sparsity pattern where typically you will have two passes, where the first pass is used to predict what tokens you'll attend to, and the second pass is used to attend to those tokens. Now note, there are other approaches to improve.
Is the phone near this somewhere?
I have a phone, yeah.
Maybe that is what is it.
Better? Yeah. Okay, sorry. There are, sparse attention is one way to improve attention. There are other approaches that have been proposed which we will not discuss. For example, there have been alternate formulations of attention which are not quadratic with the sequence length but linear with the sequence length. There's some work on using something called summary tokens or gist tokens, where these tokens are added to the sequence and they act to summarize all the context before them. So then you can, the future tokens can only attend to these summary or gist tokens. Okay, so looking at these sparse attention techniques a little more in detail, we'll spend a little time on fixed and workload sparse patterns, but most of the time on the dynamic sparsity pattern approach. So fixed sparsity, the figure on the left is the regular attention pattern where every token is attending to all the past tokens. The dark blue here is the current token, and the light blue is the tokens that it's attending to. Whereas the figures on the right give an example fixed pattern of attending to tokens. So here typically you will have a small window of recent tokens that you will attend to, along with some global tokens to carry the global context. Now when these schemes were proposed a bit earlier when sequence lengths were smaller, what we find today with large sequence lengths and complex tasks like reasoning where the attention patterns are complex, these schemes do not work well, especially post-training. But where they're finding use now is in the pre-training phase itself. So there are some new models like GEMMA and GPT-OSS, where for a subset of layers they use a fixed sparsity pattern. The second class of techniques is workload-aware sparsity, and the workload here is typically RAG. As I mentioned, RAG, to answer a user question, first you will retrieve a bunch of documents related to that question from a corpus, and then use those documents along with the question and feed that to the LLM to generate an answer. Now these documents are, it's not clear if there is, if it's useful for one document to attend to another document. They are typically independent documents. So the property that these schemes leverage is that they only do intra-document attention. So the tokens of one document will attend to the tokens of the same document, whereas the question and the answer will attend to global information. One a secondary benefit of this is that I mentioned before that the feed-forward operation is independent for every token. With this, the attention operation is independent for every document. So now the entire LLM processing becomes independent for every document, which means you can pre-process the document in advance. You can store the KV caches outside, and at LLM inference time, you can just bring in the KV caches of the document and skip the entire LLM processing for these documents. Again, what we find in some of the experiments that we did is that if we use this as is, the accuracy takes somewhat of a hit. So what some schemes do is that, and the reason it takes a hit is that these are attention patterns that the LLM hasn't seen in its training. For example, the LLM hasn't seen the fact that some token in the middle, like here, has no attention to any other token before it. And LLMs, they can be very non-intuitive. They can learn non-intuitive patterns. For example, a very common pattern that they learn is something called an attention sink. where every token somehow always attends to the first token in the sequence very heavily. So there are non-intuitive patterns that we learn, and if you break those patterns, you suffer from an accuracy hit. So some approaches, what they do is they do some amount of training with this new pattern and up the accuracy. Something that we explored is to try to correct for this problem directly by making sure every token is additionally attending to a few more tokens. So here's a graph of what we saw is that if every token attends to just about 30 or 40 extra random tokens, then we see a sharp bump in accuracy over just pure intra-document attention. And then from there on, it's a gradual increase till we attend to more. And finally, dynamic sparsity pattern approaches. So here, as I mentioned, there are typically two passes. The first pass, you predict what tokens you want to attend to. And in the second pass, you attend to those tokens. Why does this work? We discussed the softmax operation, and it has this effect of sparsifying the weight vector, which means that most of the, if you can somehow predict the non-zero attention tokens, then you should be able to cover most of the attention weight. So this figure, I mean, if you focus on any one of the cells here, what it's saying is for any layer or any head, we see that just using the top 10% of Oracle predicted tokens covers pretty much the entire attention weight. Almost, even this axis goes only up to 75%, and most of the values are very close to 100%. The figure on the right shows the accuracy of an Oracle top K attention scheme, which again we see even if you go down to 2.5%, the accuracy takes a very small hit compared to a baseline. So with this, the problem is, of course, we don't have an Oracle. Coming up with the Oracle scheme basically does full attention to get the right tokens. So the problem becomes, how do we cheaply identify the tokens we want to attend to? And again, there are multiple schemes proposed here. What we used in one of our work streams is we leveraged this insight of cross-layer similarity. What that means is, if token X attends to token Y and Z in a particular layer, we find that it is very likely that it will continue to attend to token Y and Z in a nearby layer. And again, this is a matrix showing this exact insight where, which is basically the similarity between the Oracle tokens of two layers, and we see that most of the time it's very close to 1, and especially for nearby layers it's very high. So with this, you can imagine a very simple scheme where we take a subset of layers, we compute the Oracle top K tokens there by doing full attention, and then for the intermediate layers, we reuse those same top K tokens. Now, the performance speedup, of course, depends on how many layers you'll choose to recompute and how many you will do reuse on. This is a scheme that I just talked about. Of course, there are some hyperparameters here, as in how many layers you should select to recompute on, and what percentage of top K tokens you should use. Okay, so there's some practical challenges to make this efficient. One is that many of these GPU kernels, when they're doing full attention, what they do is they load a tile of queries and a tile of keys. And this is done because every token has to attend to every other token. So if you load a key, you want to amortize that key load across multiple queue tokens. Now, but in a sparse attention scheme, since every token is now attending to a different set of keys, potentially, it's hard to amortize this key load. So this is something that we have to fix to make this efficient on a GPU kernel, and this is done by making sure that for a small tile of queue tokens, we have a consistent top K keys. A second consideration we have to think about is that there's a concept of heads in attention operation. So there are multiple heads in the attention operation. Each is doing the self-attention operation independently, and it has its own top K indices. So as we reuse these in the next layer, if we do the basic thing of reusing the head one's top K tokens in head one of the next layer, we find that accuracy suffers. And in fact, there's nothing in the LLM architecture that couples heads that way across layers. So that's something we have to solve for, and we've tried a few different techniques here. But once we do that, what we see is, so this is an AIME data set. AIME is a data set of challenging high school mathematics problems. And before the reasoning models came through, the accuracy on these data sets used to be very low. Now with the reasoning models, what we are using here is an 8 billion model distilled from DeepSeek R1. Here, full attention, we see that about 50% of the problems are solved. When we use a fixed pattern like a sliding window, we see that that's not able to solve almost any of the problems. And what I just presented here is very close to being able to solve 50% of the problems. The second thing that's somewhat interesting here is these decode lengths. So these problems are about just 100 or 200 tokens. But in order to get to the answer, you can see how much of a reasoning chain it has to generate. This is about 12,000 tokens. It's like a chapter in a book. These are some performance numbers in attention. Again, that depends on how many recompute and reuse layers you choose. So these numbers are for some particular setting. So with that, I'll conclude. So long sequences are increasingly important in LLM inference. The self-attention operation is a bottleneck here. As the GPUs become 2x faster, we'll not be able to scale these sequences 2x. And it's still an open research area. In spite of many solutions in this space, most models today are still doing full dense attention in both training and inference. With that, I'll take questions. Thank you.
Thank you, Saurabh. Do we have a way of asking the other room whether they have questions or not? Okay, we'll start here. Okay, any questions, Saurabh, from this room? While folks are thinking, yeah, go ahead. No, go ahead. Being a non-expert in this area, I was just wondering what's a good. You showed the F1 score trajectory. It was flattening off at about 0.5. Yeah. What's a good score to aspire to?
Yeah, I think in this space it's not so much. I'm not sure if there's a very good score to aspire to. What it is about your accuracy performance trade-off. You will think about how much performance you have available and what is the best score that you can get at that performance. And for that you can try a bunch of different techniques and see which of these modifications is able to get you. So for example, if you have a certain amount of compute, you can either serve a longer sequence length, so you can do more reasoning and get a better answer, maybe using a sparser attention scheme, or you can use a shorter sequence length, but do dense attention and get an answer. So I think it'll be that trade-off.
Thanks.
Thanks, Gaurav. Just a quick question on how exactly do you manage sparse attention? Meaning, like, sparse attention as the idea is good. You are focusing only on few of the tokens in terms of doing the attention computation. But how exactly are your KV caches managed when you look at sparse attention?
Right. Yeah. So at least in what I discussed, we are not able to cut down the capacity of since every token is attending to potentially a different set of keys. So across all the tokens, you will end up using the entire KV cache. So we're not really cutting down the KV cache, which can help with batch size increases. But there are some approaches that try to limit the KV cache size as well. And what they then try to do is use the same tokens across. They basically evict some tokens out completely, and they assume that they'll never in the future have to use those tokens. So yeah, again, ends up being a trade-off if you want to evict tokens completely from the KV cache, or if you want to assume future tokens will need those tokens.
Yeah, so Govind took away part of my question, so I'll like to modify my question. So I also had a question about how does it actually impact the KV caches. So I was wondering if you could actually predict, say, or understand that some of the entries would be more useful in sparse attention in the KV cache.
can, for example, Murali was talking about this 2-level of KVK, something is off on the DRAM because it can't fit everything on the GPU. So can you do something more, I would say smarter in managing the KV cache, and what remains where, like if you partition from the DRAM and the HBM?
Yeah, absolutely, and I think there are some works on that too. But yeah, that's a very good idea. Basically, if you can, even if for at least you can predict for the next 100 tokens, you don't need these certain tokens. You can leave them on the CPU or on the host, and then bring them in as you're getting closer to the next 100, right? So if you have some predictability in your usage of these tokens, you can use that to do a 2-level storage of these KV caches.
We have time for one additional question. Yeah.
I have a question. Yeah, hi, I'm Amit, volunteer for the event. So my question is the summarization techniques that are also looking at this, reducing the prefix that we are attending to. How do they work? Essentially, that are they using a smaller model to summarize the context of the past tokens? Because using the same model, I don't know if it makes sense to summarize over it all over again. How are they working correctly?
So the ones that I am aware of, the way they work is they introduce these special tokens called summary or gist tokens, and then they fine-tune the model to learn an embedding for these tokens. So now and then they're trained in a way that future tokens will only be attending to these tokens. So somehow the model learns that if it sees this embedding, if it sees this special token, it will act to summarize the context from the past. Again, there's only so much you can summarize in one token, right? So some of them try to add three such summary tokens or 4 such summary tokens. It ends up being these trade-offs.
Okay, if there's no more questions, let's thank the speaker. So I think we've made up for some of the time deficit that we were running at. So the last speaker of this session is Professor D. Krishna Nandewada. He's faculty at IIT Madras in the Computer Science Department. His interests are in compilers, program analysis, programming languages, multi-core systems. He's previously worked at ITM Research India, and he has a PhD from UC.
Thank you. Morning everyone, it's already afternoon. Before we start, I had a quick question, check. How many students from CSA here? Alright? What is this room called? This is not the seminar room. This is the Castle and Compiler Labs. And I used to sit somewhere in that corner a couple of decades ago. Anyways, so today we'll be talking about parallelism. And statutory warning, I shall not be talking about the word machine learning except what I did just now. Alright, let's start with a bit of history, right? I mean, if you look at it, from the time Charles Babbage's analytical engine, right, first machine that came up, commercial one, IBM 704, in 2009, around 50 years, we reached petascale with it, right? In another couple of years, we reached 10 petaflops, right? And currently, the fastest supercomputer is around 1.74 exaflops. So let's think a minute. How did we get this speed, right? If you look at it, from 1993, when the 386 etc. started, right, till June 25, when these numbers were released, the speed has increased by nearly 30 million times. So does it mean that if I take my same bubble sort program and run it on the fastest supercomputer, will it run faster than what it does on my laptop, right? Most likely the answer is no, because the speed is coming from the parallelism. What we will do today is try to see if we can appreciate some of the problems in this space and I'll take some inspiration from Mark and not give any solutions. I will pose some problems and leave some more problems to imagine. All right. So let's start with the story. So there was a grandpa who lived in a village who had a piece of land. Okay, he wanted some help. So he hired 2 workers and got the work done in half the time. Right? He was very happy. His profits doubled. Then he hired 4 workers. Right? He said, okay, 2 is good. Let me hire 4. Work got done nearly 1/4 of the time. More profits. Right? And he kept on increasing by one. Maybe I'm just making it up. Around 128 workers, the profit started reducing. Right? And maybe with 256 workers, no profits, no loss. Maybe with more workers, there's a big loss. What's happening? I mean, we are increasing the number of workers, number of threads, number of compute elements, and if you look at, I mean, the moral of the story, right? The same thing applies to our own computing scenario where I can keep on increasing the number of cores, but I will not get benefits unless I use them in an efficient way, right? I have more workers, more tools. There are a lot of, see the issue with the grandpa story, when the number of workers increased, they started fighting among each other for the same set of tools. There was more coordination to be done so that they can make something together, right? Same thing happens when you have a lot of hardware resources. I have the chores to be done has to be somehow divided among these workers. So we have tasks, we have threads, we have these many chores, and the question is how to get the best out of it. In hardware, I mean, there are a lot of things that are changing, right? The source of parallelism, processors, cores, SMTs, and if you think that, okay, you are happy with it, Moore's law, the newer version says the number of compute units that are available, they are nearly doubling every 2 years. I mean, if I'm happy, I'm able to utilize these many cores, now there is more. The memory can be shared, distributed, communication has a lot of variety, storage has a lot of issues, variety. Among the compute elements, it could be symmetric, it could be asymmetric, there could be dynamic multi-cores, right? And heat, I mean, that's a big thing, right? I mean, how do you keep your machines cool? You probably need a full-scale power plant to cool your machines. There are issues in software too. Like if you're a programmer or a software stack developer, a systems developer, you need to understand whether it's, I mean, how is the software working? Are there threads? Are there tasks? How much parallelism is there in the machine? How much parallelism is there in the application? Right? How are the synchronization getting affected? I mean, is the synchronization between threads? Is the synchronization between tasks? What is the cost of synchronization? Where are the barriers? How to implement mutual exclusion? How to send messages? How to receive messages? Right? If those of you who are happy with your own codes, serial codes, and have reasonable confidence, will you still have the same confidence when you write parallel programs? There are deadlocks, there are data races, right? And to just top it all, Amdahl's law says the performance improvement is still limited by the serial fraction. Do you really want to work in this space with so many issues? Unfortunately, we don't have an option. The way the hardware and software things are changing, we have to pick them up. We have to work in this space and support the infra here, right? All right. What we will do, we will try to highlight some interesting problems in this space. I will use a simple line subset of OpenMP to highlight the problems. For those of you who are not familiar with OpenMP, I'll give the basic required syntax here. In OpenMP, using OpenMP is like annotations with C. okay, on top of C. So you have C language, you have some annotations. Annotations are given as pragmas. So if you write hash pragma OMP parallel and a statement S, the statement S is executed by a team of workers. Okay, you can specify the number of workers. Okay, so if there are n threads or n workers, as n instances of S will be executed. Right? OpenMP has a construct called hash pragma OMP for. It's a work sharing construct. What happens is that the iterations of the for loop are shared among the threads. If you have created a region with 10 threads and you run this for loop, hash pragma OMP for annotated for loop, the iterations are divided among these 10 threads. There is a pragma called hash pragma OMP barrier which synchronizes among the threads or workers. Okay, I'll be using the words threads and workers interchangeably. Okay, here's a simple example just so that our understanding of the language is fine. I have a hash pragma OMP parallel region. So the main thread reaches here, and depending upon your parameters, some n threads will be created, including the main thread, and total n, and this S1 will be executed by all n. Then there is a barrier. All the threads wait for each other. Okay? Pay attention, all the threads wait for each other. And then I have a for loop whose iterations are shared among the n threads that are created. So here n threads are executing S1. Here the for loop is shared among n threads. Okay. And then they wait for each other, and then S4. S4 is again executed by just the main thread. Is that fine? Simple syntax. Syntax to create a region, syntax for work sharing using a for loop and a barrier. Okay. What I'll do now is I will go over a few patterns that we have found in different programs and see if that excites you. Okay? Let's look at a code. I have a serial loop. For simplicity, I am just showing it as two iterations. It could be a serial loop. Inside a serial loop, there is a parallel region. Okay? Let us say that the number of threads I have is 4. Okay? And let's assume that say I have 4 threads, and in iteration 1, let's assume thread 1 takes 30 units of time, 20, 25 and 10. Okay? They wait for each other at the end of the parallel region, and again iteration 2 starts and threads take 20, 30, 25 and 40. It looks good, right? If you pay attention, the total work done by thread 1 is 50 units of time, worth of time. Thread 2 also 50, thread 3 also 50, thread 4 also 50. But how much time will this program take to execute? It is 30 plus 40, 70 units of work. In terms of work done by each thread, it's 70 units, only 50 units, but the total time taken is much more. So overall there is equality, but parts of unequal work. In such a pattern, can we do anything about it? Right? So at some level, you may see that there is some imbalance of loads. There is some idling and some imbalance. Yeah. So here is the first question. How to find such imbalance? If you look at it in this, from a compiler perspective, this is the same piece of code executed by all the threads. Okay? How to identify such imbalance? And do we need human annotations or can it be automated? Can some tool be of help? Let's think about it. So let us say, I'll say, look, why do I have the barrier? Why don't I remove the barrier fully? And then thread 1 will take 50 units of time. Thread 2 will start 20 plus 30 immediately, 25, 25, 10 and 40. So we can finish in 50 units of time. But if I remove the barrier, is it safe? Let's think a very simple scenario, right? Let us say thread 2 depends upon something thread 1 computes very late. And maybe thread 3 depends on something that thread 2 computes here. So as a result, and similarly there is a difference between T3 and T4. As a result, if I just remove the barrier, thread 1 has not yet computed, but thread 2 uses the value. Right? It would be ideal, cool if I can remove the barrier, because the overall, the critical length would be just 50 units of time. But if there are dependencies like this, it can lead to incorrect translation. Okay? So moral of the story is it's good to think in parallel. Balancing the thread workload among threads, even across kind of let's say parallel phases, is important. But we don't have to always worry about I mean, so the programmer has put a barrier, don't go across it. The programmer may put a barrier, maybe it's not required. So we need to do some dependence analysis and find out, hey, which barriers are required, which are not required. Okay. I will look at one more pattern now. Okay. Here is a pattern. There is an outer while loop. Okay. So this is a typical pattern that we find in parallel and distributed codes where you have rounds of computation. In each round you do some computation, and after the end of the round you do some checking, am I done or not, and continue. So that's the outer loop. And the inner loop looks like this. I have a parallel loop, and let's say I'm going over vertices of a graph. Okay? So I'm going over all the vertices. If the vertex is active, do something. And what am I doing? The inner loop is a serial for loop. The time taken by the serial for loop is proportional to the number of neighbors. If you are processing a Twitter graph, let's say iteration 1 and 2 are processing mine, and without knowing any one of you, pick any one of you, and some other thread, let's say is picking the threads of Trump and Modi and Biden, then the work done by them is far more than the work done by the thread which is doing mine and your vertices. Right? So in this pattern you'll see there are multiple rounds of computation. From a compiler point of view, every thread will do the same work, or assuming these number of iterations are divided equally. But how do I divide them equally? Just if I divide the number of iterations equally, is it enough? It's not, because the work done could be different, right? So the point is, the processing cost for each vertex is not the same, even though the code is the same, right? And just to make it more exciting, the processing cost of a vertex can vary across rounds. In one round this vertex could be active, in the next round it may not be active, right? And it's not easy to reorganize the full data to say all the active vertices I'll bring to the front. That's a lot of overhead, right? What can we do about it, right? I think in one of the previous talks, it was mentioned, see, statically reasoning about them is very difficult. Absolutely the same case here. How do you load balance such a code statically? Because only at runtime I will know which vertex has how many neighbors. Vertex 1 has k neighbors, vertex 2 has m neighbors. I know it only at runtime, the exact values. And depending on the cost of the number of neighbors, the actual work will be determined. If I do the full analysis in runtime, it's too expensive. What do I do? Right? So ideally we would need a combined static and runtime analysis, where the static analysis can aid the runtime analysis to figure out the actual cost, and then accordingly make the decisions at runtime. Right? Here is one more pattern. Let us say I have, the syntax, I was just lazy, I didn't write the full for loop syntax, but yeah, let's say I have a for loop like this. For I goes from 1 to n times t, let's say I have t threads. Okay? And if I have t threads, let's assume the number of iterations are n times t. That is, a simple distribution can be done to divide the iterations equally among all the t threads. Everyone will get equal number of iterations. And again, the code is irregular. The work done by each iteration is different. Can be different. One can say, okay, how do you distribute this? You could say, okay, I'll give first n to thread 1, second n to thread 2, next n to thread 3, and so on. That is called a standard static schedule. We can think of cyclic scheduling. 1 is given here, 2 is given to the next thread, 3 is given. So this is cyclic scheduling and so on. We can think of dynamic scheduling too, where I'll give each thread some iterations, and whenever a thread is done, it gets more. So it so turns out, in such star parallel programs with irregular loops, just this scheduling, static, cyclic, or even the dynamic scheduling, we see there is a lot of imbalance. Dynamic looks cool, right? I mean, it says whenever you are done, take more. I mean, the issue becomes if there is a central boss who is sitting, and every time you need more work, you go and request the boss. There's a lot of overhead involved. Because if multiple guys are asking for the work, there are locks involved. Things can slow down big time. Right? When I ask for iterations, how much I'm asking for work. How much work should I ask for? Should I ask for 1 iteration, 2 iterations? When I ask for iterations of work, how do I know how much time you will spend in that iteration? If I ask for, say, 2 iterations, they are huge. Maybe I should have only asked 1. Right? Some of you might be familiar with this idea of work stealing. What is work stealing? Work stealing says there is no central boss. There are n workers working. Whenever one worker is done, she will go and ask her neighbor or one of the neighbors, give me some work. Sometimes they won't even ask, they just steal. Okay? And this is slightly better. But let's think, if I have to steal, 2 questions arise. How much to steal? From whom should I steal? Right? It's easy to see how many iterations have been finished by each thread. So maybe you have 10 iterations left, you have 3 iterations left. Whom should I steal? See, talking about work stealing based on history, on how threads have done work, will not work for irregular programs, because there is no, just because you have been working with smaller iterations so far, how do you know the next iterations are also small? There is no guarantee. Right? So the basis of stealing and cost of stealing also takes time. When I steal, it shouldn't happen that one who is working is getting disturbed too much. Right? So the basis of stealing, how many iterations to steal, should I, instead of looking at number of iterations, why don't I steal based on the amount of work left? How do I find out the amount of work left? And that too, I mean, can I do something?
so that at runtime I can compute how much work is left for each thread, and then the one who has the maximum work, let me hear him or her, right? Okay, so see, the moral of the story is it's important to keep the issues of scheduling in mind. Work stealing is great, but instead of looking at the number of iterations or some such static metrics, stealing based on the remaining workload can be cool. Okay. Here is one more pattern. I have a parallel region in which I have two parallel for loops. I finish one parallel for loop. I assume a bunch of threads, finish this parallel for loop, wait for each other, and then go. If you see, I'll ask myself the same question I asked just before. Let us say I, as a thread, have finished my share of iterations. What should I do? See, there's an issue with stealing. Let us say I want to steal from him and he has only one iteration left. So if I steal from him, probably not good. And that iteration happens to be a large iteration. What do I do? Sit idle. Why don't I do one thing? Knowing well that stealing can help a bit, but when I cannot steal, what do I do? Right? Because stealing itself, work stealing itself is not giving me confidence that I won't be idle. Okay? Kya kare? Let's borrow. See, beg, borrow, steal. I don't want to beg. Okay, I tried stealing, now I'll try to borrow. Maybe next time we'll try to beg also, but yeah. So here what we are doing, let's say across the barrier, I have some more iterations to do. Can I borrow some? Can I borrow across the barrier? What's the advantage? I'm done with my work. You still are doing your work. Let me go and pick something across the barrier. And then of course you will ask the same question. How much should I borrow? Because if I borrow too much, what will happen? Now you will wait at the barrier. If I borrow too little, I'll keep on, because borrowing will also keep on, I have to check if someone is free or not. So I have to kind of waste cycles. So I have to borrow carefully, because I don't want to introduce new imbalance, right? So we call, such a barrier can be called as an elastic barrier. Yes, there is a barrier. You should not cross the barrier carelessly. So this is like in India, you will see there is a barrier at the railway station, right? If this is many places, it's always down. They never lift it up. So you look at it. If there is no way train coming, you go under it, right? Don't do it. But it's kind of like that. Like it's like saying there is a barrier already, but if you can borrow work across the barrier, try to. Okay? Then of course the question is, how do I know the work I'm borrowing is ready to be executed? There can be dependencies. I may be accessing A sub I and the barrier was there so that thread 2 should have finished updating A sub I. If I start doing the work, I'm in trouble. How do I know at runtime whether you have finished executing thread, updating that A sub I or not? So this cost of coordination has to be carefully handled. And amount of work I choose could be depend. See, there are two parts, right? I need to know that you have a lot of pending work, not number of iterations, lot of pending work. Also, the thing I pick up is not the number of iterations I should pick up, but the work I pick up. So basically, I have to get an estimate of the remaining work of others and how much work I have myself. Both not number of iterations, but some other units of work. Maybe
worst case how much time it will take to execute. Okay? So the moral of the story is, don't just focus on the current phase, that is before barrier. Be prepared to look beyond the barrier. Okay? And we have to respect the dependencies. And remaining workload again can be a good candidate, a good tool for us to understand the right amount of work to pick across the barrier. Here is one more pattern. See, when we talk about parallel loops, right? In OpenMP, people talk, we have parallel loops, and let's say a programmer wants to do something like this. She has n iterations to be executed in parallel, and she wants to do some computation. All the n iterations have to wait for each other, and then do something more, do a reduction, and based on this computation, do something. So the programmer's intention here is the barriers should be used to synchronize across all the iterations, all the parallel tasks. But OpenMP doesn't allow you that. Syntactically it may allow, but if you write such a code and run, I think the latest OpenMP compilers are throwing an error, but if you just put it inside a function, it won't throw an error. That's fine. The point is, OpenMP says synchronization between threads. The programmer or the program logic is that synchronize across the tasks. So what can happen is that if you have divided, let's say two iterations each, then the synchronization is happening after you have executed first iteration, you have executed your first iteration. You have not completed two iterations because the way the for loop executes, first iteration, both have reached here, there is a barrier. The barrier should have been executed across after everyone has finished the top part. As a matter of fact, if you write such a code, again as I said, put it in a function and call it. It can give right answer, it can give wrong answer, it can crash, it can hang. All four possibilities are there. Right? So it's important to understand whether the synchronization is between threads or tasks. If the programmer wants synchronization between tasks in OpenMP, right? Basically the programmer is thinking, oh, every task will be executed by a unique worker. Every task will be executed by a unique worker. That's a good model to think about, right? Why should the programmer worry about how many threads are there? Let the programmer only think about the program logic and let the compiler and runtime worry about how to map them. But the semantics shouldn't change. Semantics should be such that every task is executed by a unique worker. Okay? And then if you want to do that, the moment we have to worry, the moment a thread hits a barrier, we have to see should it start executing immediate code after it or the code before it. For example, I'll go back to the previous slide. Thread 1, let's say, comes here, hits the barrier. It has to see that, oh God, I shouldn't go forward, I should rather execute the second iteration. Right? So the continuation to be executed at a barrier has to be carefully computed by the compiler if we want to support such a system, right? So should we allow such a synchronization? The answer is yes, why not? As a compiler writer, I would like to support different paradigms of thinking and programming. That synchronization we talked about is all to all iterations wait for each other. What if we are talking about not all to all, but point to point? Can we support it? What about the overheads? Can this lead to deadlocks? Right? Points to think about. Anyway, I'll skip there about the patterns. I'll summarize my story here. Think in parallel. We have to be careful that parallelism in the program should match that of the runtime. Balancing workload is important. We want to avoid creating redundant tasks redundant joins, redundant barriers, redundant mutual exclusions, anything redundant. And because the cost here is way more than serial programs, we want to keep the data near the place of computation, owners' computes, etc. We have to keep the issues of scheduling in mind. We have to keep the energy costs in mind, right? These are some of the issues we have to keep in mind if we want to talk about performance and programmability. Okay? And yeah, pay attention to the serial part also. Anyways, so the manual optimizations are good. We are working on automated tools involving compilers and runtime to address some of the challenges we talked about. And our group PaceLab works on compiler optimizations and language extensions for both traditional HPC computations as well as business applications. And yeah, I'll stop there with one thought, just one thought. If we keep on working in the way we are, let's think if we are ready for the next wave that is coming. See, once we have Jetta scale, further up, are we ready to utilize that computation, right? I will leave you with that thought and encourage you to think more about these optimization issues. And I'll take any questions if anyone has.
Thanks for this nice capsule talk before lunch. So, on a lighter note, why don't you hire a manager? Pay him well, he will manage all your workers.
But see, manager becomes the central point of failure because everyone now the workers have to report to the manager instead of the grandpa.
I have many.
You have many. Oh, that's a good idea. Ask them to send their CV to me.
Okay, so on a realistic note, so this manager could be a thin layer.
Correct. You can have multiple managers.
There could be a thin layer, and I see that it's not compiler, it's basically some runtime management which is doing. So this runtime management could be a some thin layer which is kind of maybe some sort of shared variables where everybody is saying that where they are, what they are doing, and then everybody else can.
Absolutely. Excellent question. So, like the question I asked to Mark, how many layers of memory should we have? Similarly, they can have many layers of management also, right? And it's unclear to me if there is a kind of an ideal way to create the number of layers of management. What's the best way? We still have to figure out. Maybe if I give an application, we may be able to come up with a certain hierarchy that will work the best for that. Okay, but I think it's an excellent idea to think about.
I have one question if there isn't one in the audience. Yeah, go ahead.
So Krishna, you talked about executing beyond the barrier and doing it carefully. So are you implying here speculative execution and runtime support or hardware support to detect dependencies and squash the computation system beyond the elastic barrier, not beyond the barrier?
See, Professor Govind, thanks for the question. I did not give an answer.
Yeah.
Right?
Do you intend to give one?
I'll answer it in two different directions. It so turns out that particular work we had implemented it. It was a couple of months back. It got accepted ACM TACO. We are not speculating. We are only executing. So we call it as elastic barriers, and we will execute the work only if we are sure that the work is ready, right? However, having said that, I think speculatively executing would be a great option for the following reason. What we found was that continuously checking if the work is ready or not, for some workloads it was causing a fair amount of overhead. So speculatively executing and maybe squashing just that part if required can be a great option. We didn't think about it that way. The students graduated, but but I think it's an excellent point to think about. Thank you.
Just one quick question. So this is not a program analysis question, but the examples of imbalance that you described are all because of the nature of the code and the patterns that you illustrated. Right? But there could also be imbalance that arise out of deployment constraints. Like even if you look at a multi-socket server, latencies to memory are not uniform. If you look at a distributed system, then all bets are off in terms of predicting the execution time of each individual task. So is that an active area of research as well to figure out whether some of these techniques can be applied there?
See, I mean, the way we work, we have been trying to solve simpler problems to start with. And there are so many. What you're saying is kind of one step ahead, and an absolutely important area too. I mean, just for the students, right? This multi-socket, multi-node systems can bring in such beautiful issues. I'll give you a very simple scenario, okay? We were working on a problem. I had, let's say, 2 threads. One working on node 1, one working on node 2. I slowed down thread 1, the frequency of node 1. So thread 1 slowing down is okay, but it slowed down the execution of thread 2. Think why. Again, I repeat, I reduced the frequency of node 1 because I wanted the thread 1 to go slow, but thread 2 started running slowly.
Dependency between the 2 threads?
Dependency as in?
So the thread which is running on node 2 was dependent on some data which was produced by node 1?
Let's say there is no such, I mean, it's not a producer-consumer type of dependency. It so turned out just 2 days back I was explaining this in the class and exactly the same answer also came. Think about it. Yeah.
Maybe the resources are more used by thread 1.
Sorry?
Resource capacity more is used by thread 1 and therefore thread 2 is going slow.
Why is thread 2 getting slower? I mean, why should the time taken by thread 2? See, memory, they have their own memory. I mean, it's not that I've reduced the frequency of node 1. The memory is still running at the same speed. Memory is not slowing down. There are no other resources, let's say, except memory. Anyway, I'll let you guys think.
Maybe we'll take that back.
Yeah, exactly. Let them think.
So thank Professor Krishna.
Thank you very much. Oh, you want a certain background, right? Oh, you're blocking the background. Thank you.
All right, thank you so much. Yep. Before we make quick announcement, there's a group photo in the garden before lunch. So